Jikalau ku melihat gunung laut membiru, ku lihat indah wajahnya, Indonesiaku. Jikalau ku mendengar burung-burung bernyanyi, ku dengar merdu suaranya, Indonesiaku. Kulihat sinar matanya menyinari cakrawala, menguning hijau alamnya, mewarnai bumi Indonesiaku. Jikalau ku melihat gunung laut membiru, ku lihat indah wajahnya, Indonesiaku.
See the world is incredibly beautiful. Sometimes it's hard to see beauty. All we see is in imperfection. This world that we live in. This is beauty all around us. Beauty that can only be seen with open eyes.
Dan diharapkan handphonenya di-silent-kan. Diharapkan kepada komtinya agar segera menghubungi temannya untuk ke sini, dikarenakan agenda kita akan segera dimulai.
Cek satu.
Cek. Satu. Agak besarkan dikit, Bang. Tes. Satu.
Cek. Ini tak menu.
Tes. Baik, sekali lagi diharapkan kepada komti agar segera telepon atau menghubungi temannya untuk ke sini. Tes.
Cek.
Sekali lagi diharapkan kepada teman-teman yang ada di luar
Well, ladies and gentlemen, may I have your attention please? Our second day of this event is about to begin. Please have a nice seat and back to your position. We cordially invite you to be seated. Assalamualaikum warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen.
Salam sejahtera bagi kita semua. Welcome again on the second day of the second International Conference on Sciences and Applied Physics 2022.
First of all, let us pray and praise to God Almighty because over the blessings and graces we can gather at the second day of this event.
Second, let us greet to our beloved Prophet Muhammad sallallahu alaihi wasallam, who had brought us to the path of light and live the darkness in this life. Now, we are continuing to second day of International Conference Science and Applied Physics with plenary session with an outstanding keynote and invited speakers.
Excellencies, participants, ladies and gentlemen, we would like to invite to the stage our first invited speaker for today, Dr. Michio Kawamiya from Japan, Agency for Marine Earth Science and Technology Japan. The invited speech will be moderated by Mr. Asar Mudalubis, PhD.
Without any further ado, please welcome to screen Dr. Michio Kawamiya and Mr. Asar Mudalubis, PhD.
Assalamualaikum everyone. Alhamdulillah. We'd like to thanks to Allah Subhanahu wa Taala. So today we having here again at the second day of ICSAP Conference 2022, and salawat and salam to Nabiullah, our messenger Muhammad sallallahu alaihi wasallam. Good morning everyone. Honorable Dr. Michio Kawamiya from Japan Agency of Marine Earth Science and Technologies, and then we also have here our college Professor Qiu Qiang from Southern China Institute of Oceanography, and then I expect also here already coming in online Professor Dr. Sri Yuda Setiawati from Innovation and Research of Agency Indonesia, BRIN. Lastly, who the next speaker? I forgot the name. Sorry, Professor Yang keynote speaker, Professor Yang Qiu from Swansea University, United Kingdom. Good morning, Dr. Michio. How you have been? Azamas, Genki desu ka?
I'm very fine, thank you.
Okay. So, can you hear my voice actually? Can you hear my voice?
Yes.
Okay. So, today in this first session we have Professor Dr. Michio Kamigawa. He is now Principal Researcher Department Research and Institute for Global Change, JAMSTEC, and also he Director at Center for Environmental Modeling and Application. His research interests, I think, is related to climate change, including modeling of carbon cycle and Ocean Ecosystem and Global Warming Project. So we are very pleased to having here you in this morning, Dr. Michikawa. As you may know, maybe your time presentation, I think more or less 35 minutes, including key A, question and answer. I will divide in this session into two stages. The first you have presentation and then followed by question and answer by audience. Now we have audience both in offline and online. I think you can see also in our Zoom application the participant. Now is I think time is here. Please start.
Okay, can I share my screen? I see my screen. The presentation board. Okay.
Yeah.
Seems it's working. So I'll be starting. And thank you for introducing me and inviting me to this important meeting. My title of the presentation is Climate Change Projection by Six Climate Models and its application toward ocean impact assessment. And my name is Michio Kawamiya. From JAMSTEC, Japan Agency for Marine Earth Science and Technology, and a bit more self-introduction, very briefly. My background is physical oceanography, and spent some time in Germany as a postdoc, and joined my current workplace about 20 years ago. And now I'm head of the group developing a climate model for projecting climate change. And I'm also involved in IPCC activities in Intergovernmental Panel on Climate Change, and also Vice President of Japan's Geoscience Union. Okay, and I'm going to present some of the recent perception about climate change. This is the very fundamental figure for global mean surface temperature, and which clearly shows that the globe is warming. It's surface temperature averaged globally, starting from the middle of 19th centuries up to, approximately now. And you can see that the temperature is rising, and the lower panel basically shows the same data, but averaged over every decade. And you can see that every decade is the warmest compared to the precedent decades. So four consecutive decades, which is the warmest from the historical data. So it's impressive, and it's clear that the climate is changing. And including the figures, including a figure in the previous slide, many of the figures are from this report, which was published last year from IPCC, Intergovernmental Panel on Climate Change. And well, because I'm involved in climate model development, and main presentation is about simulated data. But this is observation data showing the time series of carbon dioxide concentration, which is the cause of the climate change. And it starts from 1958, where direct air sampling has started. And you can see that there is a small ups and downs due to the photosynthesis by the land vegetation in the northern hemisphere. But overall, it's increasing very steadily, like this, starting from about 300 ppm to more than 400 ppm nowadays. And the pink line shows the difference between northern and southern hemisphere. And because the human activities are more concentrated on the northern hemisphere, it's always northern hemisphere has always the higher concentration of CO2, and the difference is rising, providing a piece of evidence that this increase is anthropogenically caused. And the increase of CO2 concentration is, of course, brought about, caused by the emission of CO2, and this shows then in turn the time series of emission. And the main cause is, of course, the combustion of fossil fuels like coal and oils. But I'd like to stress that land use change is also a significant cause of CO2 emission. Land use is mostly means deforestation. So cutting the trees is a significant cause of CO2 emission. And we saw that temperature is rising, but how about the rain? And this is data from Japan, not from Indonesia, sorry. But it shows the number of days with precipitation more than 100 millimeters per day. And as you can see with the red line, there is a clear upward trend for the heavy rains, and many scientists think that climate change is at least partly responsible for this increase, because with higher temperature, you can the air can contain more water vapor, leading to leading to the increase of heavy rains. And those are the climate up to now. And for predicting the future, you need a climate model. And the concept of climate model is shown in this slide. So climate model is a kind of computer program or computer application where you teach the computer in a mathematical formula the processes forming the climate, including the solar radiation and the exchange of heat between air and the ocean, and the motion of the air or ocean water, and many others. And those are formulated in a mathematical way like this. Well, you don't have to understand this, but just for reference. And those equations are calculated on a globe, and by dividing the entire Earth into small grids, as shown here. And I understand that the audience includes many kinds of people, like scientists and people from industries and finance and so on. And some people sometimes think that climate model is a kind of artificial intelligence type of application where you feed a lot of data into a computer, and then somehow the computer predicts the future temperature or something. So that's not quite right. It's a physically based prognostic model, so you can trace the cause for all the climate warming. Oh, sorry. And this is one of the results that was obtained by the climate models. And the black line is observation, as we saw in the very first slide of this presentation. And brown is a combination or average of climate model projections obtained by many climate models from across the world. And the pale shade showed the range of uncertainty. And on the other hand, this bluish line is the result of the simulation where you assume that there is no increase of CO2 concentrations. And it turned out that you can never reproduce this rapid warming in the latter half of the 20th century if you don't consider the CO2 concentration as in this simulation. So well, this kind of result led to a strong conclusion of the last report of IPCC that the climate warming is caused by human activities. And that was the most impressive message from the last report of IPCC. And for, well, that about the global warming up to now. And for projecting the future, you need some kind of assumptions for the future emission of CO2 by human activities. And those are shown here. And this, this is year, and this is the vertical axis is emission amount. And this line shows the kind of business as usual scenario where you don't impose any regulation on CO2 emission. And those lower two lines are the scenario with more or less stringent mitigation measures. And this is, so the light blue shows the scenarios corresponding to 1.5 degrees target, and this one corresponds to a 2.0 degrees target. And the result is shown here. So starting from this scenario, you can get this result. And if you don't impose any regulation in the business as usual scenario, the warming at the year 2100 is almost 5 degrees higher than compared to the pre-industrial era. And these are I told you that these two scenarios are corresponding to 2.0 degrees target and 1.5 degrees target, and actually the warming resulting from climate model simulation shows that the increase is like that. And here I'm showing a animation for climate warming projection obtained by our climate model, which is called NIROC. And this slide will be moving, and this shows the year, and reddish colors show the warmer areas compared relative to the end of 19th centuries, and blue color. So it's still 19th centuries, and so blue and red are more or less balanced. But around the year 2000, well, the entire globe becomes reddish. And especially in the Arctic region, the warming is very prominent. And this is again the last moment of the animation that I've shown in the previous slide. And the global warming is about 5 degrees or so, as I mentioned, under the very high emission scenario. But with a very stringent climate mitigation, the warming at the year 2100 is like this, and the difference is obvious. So also the necessity of climate mitigation, at least to a certain extent, is obvious, I think. And the 5 degrees difference is almost like the difference between the present climate and Ice Age climate. So Ice Age is about 5 or 6 degrees cooler than the present day climate. So in other words, seen from the end of the century, and under the highest emission scenario, the today Earth is almost like Ice Age. So the difference is obvious, I think. And those were the projections for the atmosphere. And the IPCC report, of course, includes some projection data for the ocean. Well, this is again atmospheric temperature, but this is Arctic ice. And under the highest emission scenario, the summer Arctic sea is almost ice-free around the latter half of this century. And also the ocean acidification is going on. And the global mean sea level is going up, as shown here. And the bad thing about sea level rise is that it has just begun, and even with the stringent climate scenario, even with a stringent CO2 emission scenario, it is known that this will keep going up, and around the year 2300, the sea level rise can be more than 2 meters or so, even with the stringent climate mitigation. And with a business as usual scenario, it's of course much worse. And this is again an animation for Arctic sea ice, and it's a bit complicated, but this is America, and this is Siberia, and this is Europe in Greenland. And so the white areas show the extent of sea ice. And again, this is here. And around, so coming into the 21st century, you can see that the sea ice is gradually disappearing. Well, this is again under the highest emission scenario, and it only shows the summer extent of sea ice, and you can see that it's gone in the latter half of the 21st century. So the global environment is changing quite rapidly, especially with the highest emission scenario. So again, the necessity for stringent mitigation is obvious, I think. And this is about another aspect of the ocean. It's about net primary production, so biological production by phytoplankton, which is a base for fisheries and other activities. And until quite recently, scientists thought that the productivity will be decreasing in the future, as shown here with the with the blue rectangle square. So this is year, and the zero line means the productivity doesn't change. So it signified models, well, about a decade ago, predicted. Many of the models predicted that the productivity is decreasing, but recently the situation is changing, and some models predict increase, and some models decrease. And this figures shows the results from our own model, MIROC, and our model shows with this red line that the productivity doesn't change much, And this not because nothing is happening in the ocean, but a lot of things are going on. And due to the climate change, you have a decrease as shown with this black line. But on the other hand, you're adding a lot of nutrient to the biosphere by utilizing fertilizer for agriculture, and that flows into the ocean, and that has impact for increasing CO2, and those two opposing effects are canceling out, and as a result, the net primary production is not changing much. So this is the world map for the effect of nutrient and also aerosol transport onto the open ocean. And this is showing the net primary change due to climate change. So in many places, with climate change alone, the primary production is decreasing due to the strengthening of stratification in the ocean. So, but the problem, there is a problem if you want to utilize those projection data for climate mitigation measures, because the resolution is too coarse. So a typical resolution for global climate change model is like 100 kilometers, and that is not quite useful for, say, people from the local government involved in the measures for climate adaptation. So scientists are making efforts to make the data more finer resolutions using models called regional models. So it's a regional model is a climate model dedicated to a certain area. So in this panel, areas around Japan, and so the region is limited, so you can make the resolution much higher, like 10 to 20 kilometers. And you have the kind of artificial walls around here, and information for this artificial wall will be given by the global climate model, as I shown in the previous slides. And this shows, and we have Japanese scientists recently made a huge data set by utilizing this kind of method, which is often called downscaling. And the resolution is much finer, and this is an application of such data set showing the future change in the maximum precipitation averaged over the very large river basins. So the size of each cells like this is about a few tens of kilometers, and when the resolution is this high, it can be useful even for the people from the local governments doing climate adaptation activities. And that is also the case in Japan, and some of the data are reflected in the actual policy making. And time is limited, so I'm skipping these figures. And right now, our downscaled data set does not include the ocean data, but we are planning to enhance the data set by including our ocean model generated by the framework shown here. So we have 3 different types of ocean models at the same time. So a relatively coarse resolution model for the globe, and middle resolution model dedicated for the North Pacific, and Indonesia is here. So this model has future data for Indonesia. And we are from Japan, and we are focusing on the areas around Japan. So finest resolution model is dedicated for areas around Japan, and this ocean projection data generated by this system will be published within this year. That's our plan, including those data shown here. And again, time is limited. I'm skipping these figures. So this shows there are some varieties of projections, but the time is limited. I'm skipping. And I understand that there are also a lot of efforts like this, downscaling efforts all over the world, and there is coordination activities for those downscaling activities, which is called Codex, and information from Codex can be obtained from this website, and so someone from the audience may want to access this link. Okay, so that's it for my presentation, and this is what I have been stating during this presentation, so I'm not repeating this, so I'll finish here, and thank you for your attention.
Thank you so much, Dr. Michio. I think it's a very wonderful presentation. You saw up. There are many kind of data set, especially you saw example, the downscaling resolution data for climate modeling. I think now it's time to open question and answer. We will start from online participant. Does anybody want to ask from online participant? No? Maybe in this room, if you have question, go ahead, raise your hand. Yeah, Mr. Arya, please. Start from your name and then stand up, please.
Check. Okay, thank you for the opportunity. My name is Arya Akbar. I would like to ask you a question, sir. So, the current limit IPCC set is not more than 1.5 degrees Celsius for the future temperature change. As you said before, it is possible that the temperature will change around more than 5 degrees Celsius. My question is the current situation of temperature and climate is considered is the best one for our future, or we need to maybe plan for the better future? Because in the current situation in Bengkulu City, we already calculated the temperature change for the last 35 years in our lab, and the result is the change is around a little bit more than 1 degree Celsius. Mm-hmm. And one of the effect is we can see in the last several years so many locations in Bengkulu City flooding, and I think the current situation is not really good, and we cannot adapt in the short period of time for us in Bengkulu. So what do you think is the current situation is good for us now globally? That's my question, sir. Thank you.
Okay, go ahead, Dr. Michio.
Yes, thank you for your question. And well, so the CO2 emission trend is not my expert area, but what I heard is that well, the situation is better than the business as usual scenario. So better than the worst, but not strict enough. The emission cut is not strong enough to achieve 1.5 or 2.0 degrees. So the estimate is like, well, it is said that if we follow the current situation of emission cut efforts, the future warming will be a bit less than 3 degrees at the year 2100 or so. The current situation is more or less middle of the worst and the best. And people are, but of course, people are saying that there must be a stronger effort to cut CO2 emission. And as for your local data showing the 1.0 degrees over just a few years, I think it also includes the contribution from natural variation. So even without climate change, the climate is changing, going up and going down. And perhaps your data includes the contribution from such natural warming that may happen even without climate change, but also has a component of climate change contribution. So it's not quite easy to distinguish those two kinds of temperature change. But but on the other hand, scientists involved in the area of climate change projection are now realizing that there may be a limit for climate adaptation efforts. So even if you do the best, if the climate warming is too much, you cannot fully adapt the future climate. And that's what the climate scientists are now realizing. So I think that shows another reason for necessity for further emission cut. Am I answering your question?
Thank you. Maybe next question from Fadila. Yeah, go ahead.
Okay, thank you. Okay, thank you for the opportunity. My question is about this. Okay, sorry. Okay, thank you for the opportunity. My name is Fadila Humaira. I'm a geophysics student in University of Bengkulu. Okay, sir. My question about from your slide about attribution of recent climate change to human health graphic. So my question about simulate human and natural. Why can down and up? And then what's the factor about it? It's A question, and then B question, what is the solution about it? About recent phenomena. Thank you.
Sorry, to be honest, I didn't quite get the point.
Yeah. I also didn't get the point. Can you repeat again? What is your question in the short?
So,
Okay, my question about why can down and up about simulation, human and natural from your slide, the title attribution of recent climate change to human, and then what the solution about it, about recent phenomena?
So your question is why can you say that the climate change is caused by human activities?
Yeah.
That's the first question.
Yeah, maybe
And,
the first question.
yes, and first in the first half of my presentation, I've shown you a time series of climate change project simulation data. So you seeing my slide? So this is the Brownies computer simulation result, and showing the recent warming expressed by black line, and the blue is simulation without CO2 concentration increase, and scientists realized that you can never reproduce the recent warming as shown in this observed trend, and that is one of the strong basis for the statement that climate change is human caused. And some people say that the climate model is just nothing and don't believe it, but this time please believe it's physical based, and it has been developed throughout a long period since the days of Dr. Manabe, who received Nobel Prize for Physics. So it's the result of efforts of many decades, and it's physical based, and it's not, you can't believe it 100%, but it's a credible one, and this shows that the climate change is human caused, and the solution I don't know quite well, but it's about it's a task for other engineering scientists for involved in the new energy development and so on. And the solution is not really simple, but I heard that there have been a lot of improvements on the development of new types of energy like solar energy and so on, without CO2 emission, and a lot of other efforts are going on in many areas, and also the adaptation to the present to the climate change so far. You have to adapt to the change in the environment, and that efforts in that field are also going on. So the combination of many different types of efforts are needed to solve the global environmental problem. That's my feeling.
Great, Dr. Michio. Still flowing to this figure, you say, still related to the previous question is, in this slide, you saw maybe data around many decades, of course, But do you have data such like extending back like 5 million years ago? What about the temperature, for example? Is there a trend significant changing, going up or going down?
5 million years ago, I don't know, but there is a geological record back to 800,000 years ago, so almost 1 million years ago. And those geological data shows that the temperature has been fluctuating between the almost the present temperature and say 5 or 6 degrees lower. So over the 1 million years
1 million
time
years.
scale, it's 1 million years time scale. This warming is it's becoming very exceptional. So in warmer periods, temperatures like this was possible sometimes, but at least the pace of warming is extraordinary, even in terms of out of the history, over 1 million years.
Okay. Still, do you have question from audience? Yeah, from maybe participant online. Go ahead. One question still. Go ahead.
Yes, can I ask questions?
Yes, sure.
Okay, if my voice can be heard clearly.
Yeah.
Okay. Thank you, Sensei, for your explanation. It's very great presentation, I think. Before that, let me introduce myself. Haji Maste, atas nama Bagus Trimawadi. I'm from.
ありがとうございます。はい。
Hi, ohayou gozaimasu. I'm from School of Meteorology and Climatology, Kyunggi Physics from BMKG Agency School. I'm a meteorology student. If it doesn't matter if I ask 2 questions to you, Sensei.
Yeah, of course.
Okay, thank you. Okay, I'm still learning and studying at the undergraduate level. So the first question is, may I know what device or software do you usually model the effect of increase in temperature through SMAP 5 or SMAP 6 data on marine parameters, especially in the net primary productions?
We are adding ecosystem model to the climate model, and that one we are developing on our own. So we are developing our own model for ocean ecosystem. The name is we call it OECO 2 or 3, or depending on the version. But anyway, we are developing our own model in Japan, both for ocean and terrestrial vegetation.
Okay. Is that software for public?
It's open in a scientific paper, of course. And if you want to collaborate with us regarding ocean ecosystem simulation, maybe we can arrange something about that. So you can email me later.
Okay. I think later on you can discuss what related to the future project or what kind of do you want in the future. Okay, Pak Bagus.
Okay, thank you. And then my second question is there a significant effect of increasing rainfall on the land to the acidification process of carbon dioxide intrusions into the ocean? Maybe.
For the acidification, the impact of acid rain on the terrestrial vegetation. Is that your question? And well, I don't hear much about that. And well, ecosystem is not my expert area, so I can't say much. But I touch upon every part of climate change research as a research manager at JAMSTEC, and I don't hear much about that. So that means that the impact is not that large. So people are speaking of the change in the rain, but they don't speak much about the acid rain at this stage. So, well, 20 or 30 years ago, acid rain is a hot topic, but it's mainly about the air pollution and not very much about the climate change. And yeah, I don't hear much, so that's all I can say right now.
Okay, I think we should end this session. Thank you, Pak Bagus.
Aisha? Hello, Aisha. Can I ask last question.
Okay, I think it's nice. You are professor from China. Go ahead.
Yeah. Hello, Professor Mikio. This
hello.
is Chu Chang here from South China Sea Institute of Oceanology, Chinese Academy of Sciences. So just one question, okay? For your model, I'm wondering for the uncertainties, for example, if you disturb some key parameters and with your where your model was still kind of like a sensitivity test. If you change some key parameters where your model still give you, converts to the same results or give you the same predictions in future. For example, I don't know, I just try to understand some potential uncertainties because something disturb the whole system because your climate is very complex, right? That maybe disturb your whole system, change it to another, a larger thing, and that may give you something different or something,
Thank you for your question. And it's true that our model includes many parameters whose values can't be decided in a very strict sense. But if we explore the parameter values before we do the prediction experiment, so that the model can reproduce the present day climate. So, so the parameters can take any values, but there are certain limitations for those parameter values. In that, the set of parameter values should reproduce the present day climate. So it's not totally free. So, in a sense that the parameter set can reproduce the present day climate, we assume that the parameter set is more or less reliable. And based on that reliable parameter value set, we do a projection experiment. And we submit those projection data to an international project. And there are many other institutes for global change, and they submit different data for future projection. And based on that, so the difference between different institutes, they act like they can serve as a source for uncertainty range estimation. So that's how we estimate the range of uncertainty for future climate under this single.
Thank you, Professor QQ, CC, Dr. Mitio. I think it's time to close the session. We would like to give certification for Dr. Mitio. Please.
Yep. Thank you very much. Oh, I'm leaving. If I may.
今日は先生、道夫先生、今日は忙しいところ本当にありがとうございます。
どういたしまして。
はい、また今度会いましょう。オンラインでもいいです。はい、ありがとうございます。
I'd like to see you again sometimes. Yeah.
Now we are moving, I guess, to next session.
Check.
What an excellent presentation from our first invited speaker.
I think I need to quit my room first and then come back again. Can I do that?
Thank you for Dr. Michio Kawamiya for the invited speech.
Excellencies, participants, ladies and gentlemen, we would like to invite to the stage our second invited speaker for today, Professor Dr. Xu Xiang from South China Sea Institute of Oceanology Chinese Academy of Science, China. The invited speech will be narrated by Dr. Arif Ismul Hadi.
Without any further ado,
Please welcome to screen Professor Dr. Xu Xiang and Dr. Arif Ismul Hadi.
Ladies and gentlemen, let me introduce myself. My name is Arif Ismul Hadi. I will be serving as moderator this session 2 and second day. First of all, I would like to thank to Professor Dr. Qiu Qiang as invited speaker this session, and all audiences, thank you for joining this seminar session. Before starting this seminar session, I would like introduce you the speaker. The speaker session is Professor Dr. Qiu Qiang. He is one of professor of Ocean, Wave and Tsunami at Chinese Academy of Sciences, China. He has received his master degree in Fluid Mechanics College of Mechanics and Aerospace, Yunnan University, Changsha, China major. Then he got his PhD degree in Earth Science, ASEAN School of Environment, Nanyang Technological University, Singapore. Ladies and gentlemen, I would like the speaker invite this session Professor Dr. Qiu Qiang to deliver his presentation. Professor Dr. Qiu Qiang, time is yours.
Okay, thank you. Can you guys hear me? Hello? Hello?
Yes, Professor, we can hear you.
Okay, great. Okay, first of all, I would like to thank Professor Asha Lubis, who invited me to give a talk in this conference. So, which was a while ago. So I almost forget. I will give a talk today. So I prepared my slides in a rush. So if you guys feel not satisfied, I'm sorry about that. So today I would like to talk about the earthquake and tsunamis in the Sumatra subduction zone. We know Sumatra is being very seismically very active, either in history or since after 2004, or the giant Sumatra and Andaman earthquake. So from the figure showing the distribution of the historical earthquakes. So we can see from north to south, 1941, 1881, 2004, 2005, 1907, 1861, and 1797, 1833, and then most recent 2007, Bengkulu earthquake, and 2010, Mentawai earthquake. So these earthquakes occurred at different depths and with different rupture styles. So we can classify these structures into three different groups. So first, like the trench-breaking large ruptures, like 2004, the Sumatra, like maybe like in 1797 or 1833. And the second group is the blind ruptures, like 2004, 2005 Nias, and 2007 Bengkulu, and also the last one we call is a shallow tsunami earthquake, like 1907 or 2010 Mentawai earthquake. So those earthquakes occurred at different depths, and that is controlled by the thermal and chemical boundaries. And previous researchers can divide the subduction ruined earthquakes into 4 different domains. Okay, so first one is the domain A is shallow because it's a place where we see tsunami earthquake occur, and also the aseismic quake, after sleep. And then move further down, the domain B is typically a larger earthquake, like 2005 and 2007. And then move further down, is the domain C. We call it moderate, small earthquakes. So in different domains, the seismic radiation is different. For example, in domain A, we see lower high frequency radiation, and in domain B, we see moderate and high frequency radiation, and in domain C, we see the higher high frequency radiations. So today I'm going to talk more about domain A, B, C. So I would recommend you guys remember domain A, B, C in your mind, and then I walk you guys through in the following slides. So we know these earthquakes occur in different domains and have different characteristics that were generated very different tsunamis. So in the last several decades, as we learned from the tsunamis part is, we know when earthquake rupture reach to the trench, which is a shallow trench, and then we see a large or amplified tsunami hazard. So the question is why, when the rupture goes to a trench, and then we see an amplified or large tsunami hazard, right? So does this rupture styles affect this, tsunami genesis, and also what might control the tsunami generation and its hazard? So I will use Sumatra as the best examples because they hold all different rupture styles and also the associated kind of tsunami characteristics. And then that will help us understand how this connection between the rupture styles and the tsunami characteristics. So our first start is the 2004 Sumatra and Andaman earthquake and tsunami. And this event is occurred in the modern technology. So it's fully recorded by all sorts of geodetical, geophysical data, and also satellites. So, and the figure on the left, the pink area here, showing the rupture area. Okay. So this earthquake ruptured domain A and domain B. So remember, I mentioned in last slides, which is ruptured 2 domains. Okay, so it's very different and very large rupture. So this earthquake initiating the epicenter, which is offshore Aceh, and then rupture propagate to the Laos and through the Nicobar and also Andaman Islands here. So the rupture length reaches more than 1,003 kilometers 3 kilometers. And the rupture time duration is between 9 to 10 minutes, okay? And rupture area is more than 210,000 square kilometers. So figure on the right here, this red area shows the energy released during the earthquake. And there's red dots during the aftershocks. So basically, we can see the large energy release areas where we see this aftershocks, okay? And this event, which is, is a giant earthquake, magnitude 9.2, so it's affected by the whole globe on Earth. And here, the figure shows the blue triangles shows the seismometers on the Earth. So we can see the earthquake occurred in the epicenter area, and it's spread worldwide, far goes to US and also the South Antarctica. So here I showed 2 examples about the recorded seismic waves. One is in CASY, and another in east coast of USA, so CBN. So here the figure on the left showing the vertical and loss component of this station CBN, and both include the original data and also filter data. And the figure on the right showing the same similar vertical components of the seismic seismometers. Okay, for station CSY. Again, for the original and the filter data, so we can see the P wave, S wave is very clearly and recorded for this giant earthquake. Okay. Except these seismic waves, the earthquake also generates large-scale regional crustal deformation and the mass changes. So here, the yellow vectors show the far field displacement, which is a few centimeters, and the red one shows intermediate fields, which shows the displacement around some meters. And the black one shows the near field, which is in the fourth zone, shows the horizontal displacements, which is a few meters, which is very large. And the background image shows the equivalent water thickness that triggered by this earthquake. So we can see the images which affect a very large area in Southeast Asia. Okay, so this is about the geodetical and the data sets, and then from tsunami part. So here, this image records some information about the tsunami measured in the Indian Ocean. So we can see here, close to the rupture area in Aceh, the tsunami height is very large, like 15 meters, and then the maximum ground height reaches 51 meters, very high in Aceh. And then in the Sri Lanka, the height reached to 10 meters, and then in East India is like a few meters, close to 10 meters. And also for Thailand, here along the Thailand coast, here some part is a few meters, and then there's reports large ones reach to 10 meters high. So the tsunami is like in the south area is very large. If we plot this tsunami height in vertical bar, you will see very clearly how this tsunami height vary and how they distribute in the Indian Ocean. So basically, you can see here again, this is a source area close to the epicenter, and then here in Thailand, okay, tsunami height is to more than 10 meters, and then 10 meters here in Sri Lanka, and a few meters in India again. Except this, because the earthquake occurred in the modern technology, so the many satellites actually capture the tsunami waves in the Indian Ocean. For example, the topics, the JSON-1, NVSat, and GFO. So those satellites, they capture in different time and different spatial location, and that can help us to understand what the earthquakes and also the tsunami characteristics. Okay. So figure on the right, for example, this is the black ones are showing the actual measurement from those satellites, JSON-1, topics, NVSat, and GVSO. And blue is showing the preliminary results from most models. So this model try to understand what the first order or the features about what happened during the earthquake. Okay. So here's one examples about to using this seismic geodetical data and try to understand the rupture or understand how much slip occurred on the plate interface. So this two is a preliminary results using different geometry on data sets on time. They basically show the first like 300 seconds the slip occurred. Further loss of this epicenter, so its coast line is about 8 meters. Okay, and the last one here, this is the full Finland fault model, and that shows more details about the heterogeneous distribution of the slip on the fault. So we can see here, in the fault zone close to the epicenter area, the slip is larger than 10 meters, and then there's a significant slip in Nicobar Islands and very small moderate slip in the Andaman Islands. So basically, we can see the momentum rate plot here showing most of energy released over the 300 seconds and about 50 kilometers away from the epicenter. Except this model, there are many models here. I show some examples from using different data sets, using different approach. So here we can see in general, these models predict are consistent in the major slip area, but they differs significantly in the location of the maximum slip and also the maximum slip and also the location. For example, here, this showing the maximum slip occurs more close to the Aceh Island, but some slip they suggest that more close to a trench. So and also this one here, and this is one model and from the tidal gauge inversion. So basically, you can see the location is roughly the same, right? One here, and then but the actual locations of max slip and value is quite different, right? And that tells you we still this model still cannot converge, and something is going on there. Here is another one detailed model using the tidal gauge in Indian Ocean. You see here around in the ocean. So they use this data and to try to doing a tsunami inversion, try to understand the same thing, to understand the sleep on the fault. Okay. So here, figure on the right, the black one is the data, and the red one is the model. Okay. So in general, the model fit the data fairly well, not exactly, but fairly well. Okay. This model shows the sleep basically concentrated in two areas. One is close to the epicenter area, which is offshore of the Aceh, and also a second one is close to Nicobar Island, and the other moderate or small sleep, like about 5 meters, close to the Adama Island here. And one interesting thing is that in this model, they show the upper shallow and the deeper rupture that have very different velocity, rupture velocity. Okay, for example here, the upper showing the rupture velocity 2 kilometers per second, and then the deeper one is 3.25 kilometers per second. That may reflect some property of the fault, and that tells you the rupture is different. Figure on the right shows the final model how they explain the GPS data in this area. Okay. Here is a more detailed comparison about the sleep models from Michel and Bergman 2010. So again, there's a lot of models, right? There's basically, if you don't look at the details about the sleep distribution, or for example, the details, the maximum sleep values and locations, and then they all shows like they have two major sleep areas. One close to the high birth center area, and the other close to the Nicobar, right? And some portions close to Adama Island. Okay, so again, as I mentioned before, if you're looking at the first order, this sleep is not all consistent. But if you're looking at the detailed sleep, like the location, the maximum value, they all shows the different in significant ways. This is one like the most model published in 2007, and more recently in 2016, there's a budgeter using all these available geodetical, geophysical, and tsunami data, the user Bayesian, and to try to invert because we use all the data and we use a more fancy technical, and then they should give us a more complete sleep model that can explain everything, right? That's what we expect. So the figure on the left showing the sleep distribution, the final the preferred sleep distribution here. The vector showing the sleep motions. So with plate motions, okay, the upper plate relative to the lower plate motions. So the colors showing the actual sleep values. So if the more red, and then the sleep is more large, and vice versa. Okay, the more green and is more small. So figure in the middle shows how the model explains the GPS data. So basically, you can see the model explain the near field, far field, and intermediate field quite well. And figure on the right here, these blue dots showing this is the tsunami wave measured by the satellite in the Indian Ocean. Okay, two satellites, JSON and topics. And the red is their model predictions. So if you're looking at the comparisons here, actually is not really reconstruct the satellite observations. Even we think this is a perfect model because using all the data and all the improved technicals, right? So until now, all the models I showed to you guys they all assume the sleep on the megastrata, which means they assume the sleep on the plate interface, right? But is there any possibility the sleep occurred like in the upper plate, like spray fault or the backthrust, right? So with these questions, SafeRoute, they using the high resolution safe flow bathymetry, and what they found is here in the trench area, further close to the Aceh, what we can see is the actually pradum. There's a many thrust faults. For example, the major ones like a lower thrust fault, medium thrust fault, and upper thrust fault here, right? So, and with this high angle thrust fault is showing in the figure right here. 1, 2. This is lower, this is the middle, and this is the upper thrust fault. So basically, separate. They think they interpret the co-seismically this 2004 Sumatra and Adama earthquake occurred partially on the mega thrust, and then it goes to the upper thrust, which is this one here, and that may explain the large earthquake and large tsunamis. And then after earthquake, they think that co-seismically the earthquake occurred goes to a shallow part like middle thrust and lower thrust, and also some portion of the shallow mega thrust, right? So this is from the structure and the morphology, and then also some distribution of this aftershocks. And they propose two different modes of the co-seismic and post-seismic how the fault sleep during the earthquake and the after earthquake, right? After this idea, Arica, they using ocean bottom seismometer, about using 17 ocean bottom seismometer, and covering about 20 days, okay, in this area, offshore Archie, in this place where we see large slip occurring in previous slip models, right? So what they recovered from this ocean bottom seismometer, and they relocated aftershocks right in the upper plate and the two separate locations, and this actually corresponding well with the middle thrust or upper thrust as we see in last slides. So this is another evidence to support the upper thrust or middle thrust in the upper plate actually moved during the earthquake, right? So this is from the seismic and the seafloor morphology information and they propose that there's an extra aperture split fault, or this high angle thrust fault in the upper plate actually moved in the earthquake. And then with this idea, some researchers they actually include this. For example, they mentioned the force thrust here, and also there's a two extra upper back thrust, which is very complex, right? Before, in the previous slides, we see they only propose the mega thrust, which is here, the red one here, and then from the seafloor morphology and the seismicity, and then they propose this force thrust, upper and back thrust modes to in the model, and then they use a dynamic simulation and try to reproduce rupture propagation and rupture process. So here, the figure on the left showing this rupture propagation one-time slot. Okay, so the brown color shows sleep rate, which is how fast sleep on the fault, and then this blue-red color shows the rupture velocity. So we can see here, and here this rupture velocity is very large. And we can see the back thrust actually, if you include in the model, and the model tells you that back thrust actually moved, right? Sleep during the earthquake. So the figure on the right shows their final model. So here, DH shows the sleep occurred on the fault. So if you have more red, and then the sleep value is more large. And if it's white, and sleep is nearly zero, okay? And this one here showing the corresponding uplift. So red is uplift and blue is subsidence. Okay, so and these vectors showing the data and the model comparisons. So basically you can see if you still remember the sleep models I showed before, and these approximately predict the same locations where the sleep occurred on the fault, right? And if you compare with the recent, which we call a more complete model, actually in first order they are consistent, right? The location for here, like here, the maximum sleep occurred here, and both in the shallow, and the second concentration sleep here and here again. But remember, Nicobar is here, right? Nicobar is here, and then this sleep actually is a little bit further south than this model. Again, so if this first order, they compare is very similar, right? Very similar. And the same group with this author they did another very detailed dynamic simulation with this same geometry setup. Okay, so this figure basically showing the absolute sleep rate. So this is a sleep rate on the fault. You can see this is a megathrust, and this is on the split fault. Okay, and this is the moment rate functions. They compare with other models, and this shows showing the rupture speed. Okay, so basically before an 8 loss, the sleep rate is close to 2 to 3, and then after an 8-degree loss, and the rupture velocity decrease to like 1 or 2 kilometers per second, right? And this is comparison with this is a horizontal comparison with the GPS. This is vertical comparison with the GPS again. And the figure on the right showing their final sleep distributions and their comparison with previous two models, Ray and Chile. So basically, again, we can see in general, the location of the sleep distributions is concentrated two areas, one here and one here, and here, right? Again, very similar comparison. But if you look at the details, the locations like here, this is more deep, right, than this one, and this one more shallow. So again, right? So in general, first order the consistent, right? Not exactly the same. And they further argue that they did a further test about the strength of the upper sediments. So basically, what they found is they prefer a stronger sediment, and that can fairly explain the tsunami wave observation by the satellite, which is one here, right here. But if this blue is the data, okay, and their preferred model is the yellow one, okay. So if you compare them, okay, first order maybe they are consistent, but if you're looking at the peaks, they're not exactly the same, and also they have space offset, right? So what all these models either using megathrust or combine the megathrust and backstrust, they all shows quite a similar sleep distribution. But if you look at it in details, they differ in very different sleep maximum values and location, and also they don't exactly explain the tsunami informations. And this tells us that they tell us that all these models are not converged to what exactly happened during the 2004 earthquake, right? So now the 2004 is a rupture domain A plus B. Now I'm going to talk about the domain B rupture. Remember A, B, C, okay? So in 2004, I will give two examples about domain B rupture. One is 2005 Nia-similar earthquake, which is showing the pink area here, and this earthquake occurred right below the Four Arc Islands, which where around this island we have many corals, right? The corals is very nice. Actually, it can record how the net changes before and after earthquake. So if we're looking at A, figure on the right, A here. So this is the before earthquake, and then after earthquake is part of the coral head is uplift, and then still have some portions in the water. So we can see in this portion is caused by the earthquake. And then in the second case B, maybe the corals is completely uplifted by the earthquake, and in some cases the corals will be subsided right by the earthquake. So with this coral information, we have many different locations, then we can actually reconstruct the vertical displacement or vertical deformation caused by this earthquake, right? Here, like this one figure showing, left figure showing here. So this nice numbers and showing the yellow one shows the uplift and blue showing the subsidence. So this nice numbers shows the actual measurement based on the corals. Okay, so we can see the vertical uplift can reach 2 meters. Okay, the subsidence can go to 1 meters, like in Banyak Island, 50 centimeters. Okay. So this data give us a very fruitful information about what land moved during the earthquake. And during the earthquake, so with this important information and geodetic information, we can do the same thing as we see in 2004. We can estimate or can reconstruct how much sleep occurred on the megathrust. So here I choose 3 examples. So this is from the tsunami inversion, the GPS inversion, and GPS corals. Okay. So basically, these three models very, very similar. This is including the location of the slip, maximum slip, and also the patterns. Why? This is because this earthquake occurred in the, in the Four Arc Islands where we have many data to constrain, rather than the 2004 that occurred in the offshore, where we don't have much data to constrain that. So for this earthquake, we're pretty sure how much it moved and where it moved. Okay. For the tsunami, which is quite interesting if we compare with 2004, this is a plot from Jose Bushu, 2011. So figure on the left showing the same area which are affected by the 2004 earthquake and tsunami. And so here, this is a bar which shows 5 meters. Okay? And this figure on the right showing the same area, tsunami wave height affected by the Nias earthquake. So we visually can see the figure on the right effect on the 2005 earthquake is much smaller, right, than the 2004 earthquake. So the maximum run up is around less than 5 meters. This is quite small, moderate, right? Small. Now here are some images to show in the field and see how the earthquakes or the tsunamis are affect this area. So here. This is an area in southern Nias, which is called the Langudri Bay. Okay, so here there's some photos showing the houses. Here, basically the first level. Well, it's just on one level, right? The walls were almost it's not completely destroyed, right? But just partially destroyed by the tsunami waves, or maybe the earthquake, And then there's another place which is called the Sinkling, just behind the Banyak Islands, where this place suffered a different experience during the earthquake. So actually, this portion is subsided by the earthquake by like maybe like 50 centimeters. So we can see after the earthquake, these houses are below the sea level, and the water came in, and basically people cannot live in there, and this house is probably abandoned until now, maybe. And then another place in southern Similu, which is a place in Nambahan Bhakti, and this place again is this place was affected by both 2004 and 2005 and earthquake and tsunami. So if you're looking at the watermark on the wall, so this one here is from 2004 tsunami, and this is from 2005. So and then if you're looking at the 2004 tsunami is like more than 50 centimeters higher than the 2005 Nias earthquake, right? So this is this earthquake and tsunami information for the Nias earthquake, the rupture type in domain B, and then I'm going to show another very similar examples, which is more like connected to Bengkulu. Okay, so this is another earthquake occurred in 2007, Bengkulu, just offshore of this meeting place. Okay. So here again, very similar to 2005 Nias earthquake because its earthquake occurred below, right beneath the islands. Then we have similarly coral data, GPS data, and maybe some INSA data. So and this data were constrained tightly on what and where the slip occurred on the megastrata. So basically, we can see these three models. Basically showing very similar the slip distributions. One goes to the hypercenter area, another goes to below the Paga Island. Okay, so same again here again. So the magnitude and slip location patterns are very similar, and that which give us pretty much good confidence to know what actually moved and slipped during the earthquake. For the tsunami, again, very similar with Nias 2005 earthquake, which is here 2005, and 2004 Bengkulu is here. And the model of the tsunami wave in the ocean is around several meters, some meters. And then the maximum run-up height here, founded is never reaches 5 meters. So it's very similar, like in Nias is about 5 meters, and in Bengkulu is about 4 meters. So the survey location is here. Okay, so these two events is remarkably similar in either in rupture type and also trigger the tsunami wave height. Tsunami wave height. Maybe this represents this type of rupture and their associated characteristic of tsunami, right? So until now, we mentioned two types of ruptures. For 2004, the rupture domain A and B, right? For 2005, NIAS, for 2007, Bengkulu, the rupture domain only B, right? And these two, for 2004, rupture domain A and B, the trigger tsunami is very large. Like the maximum tsunami wave height reaches 50 meters in Aceh, and the max drop is reaches 51 meters in Aceh. But for domain B ruptures, 2005, 2007, the max drop never reaches 5 meters, right? So this is A plus B and B. Now I'm going to talk about a particular rupture in domain A, and these earthquakes we call is a tsunami earthquake, very typical and special. So in Sumatra, there are two tsunami earthquakes occurred in history. One is here in 1907, just offshore Nias Island. The another one here, showing the pink area here, okay? So it's 2010, which is called the Mentawai. It's more close to the time. This is offshore Pagai Island. Pagai Island. So today I'm going to talk about this, the 2010 Mentawai tsunami earthquake. So basically, the earthquake occurred very shallow, like here. This is an epicenter, and this area, this is red. Okay, red area shows the approximately rupture area, and this red dots shows the aftershock. Okay, and this blue one shows the 2007 Bengkulu earthquake, the rupture area. Okay, and this is blue dots, and the name shows the GPS station of the sugar network. Okay, and figure on the right shows the corresponding tsunami, maximum tsunami wave height in the ocean. So basically, you can see this small earthquake, the magnitude is 7.8, right? So it's for typical subduction zone, this earthquake magnitude is quite small. But if you're looking at the tsunami impact, they have a large impact in the Indian Ocean, right? So this earthquake caused a significant effect in the local community, basically most in the Pagai Island, and they caused large damages, floodings, house destroying to the local community, which is very shock. So after the earthquake, at that time, I was a research associate, research working in Earth Observatory Singapore. Actually, is I think it's 1 year or 2 years, or maybe 1 year before Professor Asia Lubis joined us in our group. So we built our international team, which is here, and this is my wife, and this is our team leader. This is Danny and Bongbong, that's me, and this Nick. What's this? I forgot his name. And this is I forgot his name again. Sorry. Herman. So we use our Analas. This is our hero. Okay. So this boat carry us from the Bengkulu and to all the islands in Pagai, Sibiru, and we spent 7 days there and try to understand and try to find the tsunami informations and cause the hazard. So what are we going to do? What we did there in the field is we try to find the evidence or left by the tsunami information by the tsunami. For example, we're going to find the flow depths, tsunami height, and tsunami run up. And this information is important to help us to understand the earthquake process and the tsunami dynamics. Okay, so with this, we work on all the islands, and we try to find this tsunami information. For example, the stones on the stairs and the watermarks on the wall, and this means a meter. And then also you can see many debris where in the field blocked by the trees. And this is our number, and then we check the measurement for tsunami wave height. We're also looking at this the broken branch, fresh branches on the trees, and that will also relate to the information about the tsunami wave when the tsunami wave came. All right. So here are some photos to show where the place was heavily affected by the tsunami wave height in Sibigung. So we can see here most of these islands, maybe partial of the islands, the trees, the coconut trees were completely washed away by this tsunami wave, powerful tsunami wave, and houses are destroyed. And that's our team leader there in the field and try to, record what happened, what we think about this tsunami and earthquake. Okay. So in this place, we took two profiles along this island, one here, A is here and B is here. So we can see, and that is a place where we take the maximum rob height, which reaches to 6 meters here in this place, which is very large as compared with the larger earthquake in 2005 Nias and 2007 Bengkulu earthquake, right? So in this field, this is our results, our product. Okay, so this red dots marks the location where we attend, where we take this tsunami measurement. Figure on the right here, these circles and the cross showing the tsunami wave height and maximum tsunami run. So what we found is here is the maximum height is not 40 meters and the run height is not 60 meters, and this is quite large. If you remember, the large earthquake in 2005 and 2007, and the maximum drop is never reached 5 meters. But this one, small earthquake, but the ground height is quite large. It's comparable even with the 2004 giant rupture. Okay, so with this information, geodetic data, we can actually build models and try to understand, like the sleep model we showed before, and try to understand how much sleep occurred on the megathrust, showing its figure here. So here we can see it basically maybe the sleep occurred around this occurred in the shallow part, and the magnitude reached 9 meters. Okay, that can explain the GPS data on the island. However, this model cannot explain
Time is 5 again.
the
5
tsunami
minutes
information.
again. 5 minutes
Tsunami
again.
information here, right? So this is the black is the data, and the red one is model. So this cannot explain. So if the sleep occurred only on the megathrust, cannot explain the measurement, also the tidal gauge. And then we have invoke another mechanism like a sentiment effect, which is this gray one, which is largely improved to model explanation to the tsunami information. So here's a model comparison between megathrust model and megathrust outreach, like we call it sentiment effect. So basically, we can see if we only consider megathrust models and it cannot reproduce the tsunami dynamics and also tsunami information measured in the field. Okay. So now we understand we need an extra mechanism to explain this, and then so what exactly happened during the earthquake? We still don't know, right? So Professor Liu Guruhu and their team, and they did a very detailed analysis about the structure in this shallow part. So what they found that they found very many high and many thrust faults, which look like here. So we see many these back and forth, these structures, which they call this pop-up. And these pop-up structures is very efficient to transfer the sleep on the megastrata to this and to increase the vertical and then increase the tsunami waves. So actually, if you look at the whole actually prism, there's many these structures, right? So let's see how it works. So basically, if you have 10 meters sleep on the megastrata, which is shown here, and then you only got 1 meters uplift, right? But you got like 8 meters uplift. This is how they propose the pop-up structures that explain the large tsunami in the Mentawai tsunami earthquake, which they can compare well with this tsunami measurement. Okay, one question is after this. One question is that is these structures common for all these globe subduction zone? So with this question in mind, we surveyed all the globe subduction zone and try to understand what is going on, there. So we take the 2010 Mentawai example again. So and then we did a detailed analysis for structures. So we can see, except these pop-up structures, we see many these high angles very fault here, right? And if you're looking at the sleep area is corresponding very well with the north sleep, which is called ultra wedge, and that made, if these guys slipped occurred in the earthquake, and that can increase or excite the tsunami hazard. That's why we see large tsunami hazard for the Mentawai earthquake. Okay, so we do
Excuse me, Prof. Excuse me. 2 minutes again.
We disturb all this subduction zone. They have the same feature, okay? Then we measure the weights of this subduction zone, and we calibrate a power law information between the maximum run-up and also the weights of the ultraweight and the moment of magnitude. With that, we can predict the maximum run-up and global scales. So we can see here in the west side and in the accretion margin, the tsunami head is larger than the intrusive margins where we don't have this we don't have actually margins. Okay. Now in the end, we propose a tsunami excitation zone in the ultraweight, which characters or which is maybe the likely the mechanism that controls the tsunami excitation when rupture goes to the trench, like the rupture domain in A plus B and also the rupture in domain A. Okay, with that, I'm going to stop my talk and take questions. Thank you very much.
Thank you very much. Please give applause for the speaker. Thank you very much, Prof. Kyu Kiang, for giving such as interesting and informative presentation. Now we are going to the next session, which is question and answer. To questioner, please raise your hand and mention your name.
Yes. Okay. Thank you for the opportunity. Okay, sir, Professor Kyu Kiang. Hello.
Sorry. Yeah.
Okay. Okay, my name is Fadila Humaira. I'm university. I'm student University of Bengkulu, and then the Sanghao for you.
What? Sorry.
Good morning, Zhou Sanghao for you.
Oh, 早上好. Oh, okay, I got it. Thank you.
Okay. My question is about Cesar Mentawai fault. So, what's your response, Professor, about the Mentawai fault activity as a trigger for the tsunami? Because Bengkulu Province, Indonesia, in Sumatra is very close to the threat of this hazard. And then how long this is take for the tsunami to reach the coastline of Bengkulu, Sumatra? And then what's the mitigation we can do? Okay. About
okay.
Cesar Mentawai fault.
Mentawai fault. Let me repeat your question, okay? So you want to know the Mentawai fault. So you mean the backthrust? You mean the backthrust behind the Pagai Island?
No, I mean about Mentawai fault activity very close to the threat, because have saying from
which Mentawai fault? I don't get it. Which one are you talking about? You're talking about the backthrust behind the Pagai, or the megathrust, or the Sumatra fault? I'm not sure to understand.
Sumatra fault by Mentawai, in a way. Same like your presentation.
Mentawai fault. Asha, can you help me? Which fault is he talking about?
I can help you. Maybe the question, I guess, as you mentioned, there are two at least sources for the earthquake in Sumatra subduction zone. One from megatrust, and then another is from backtrust. We call Indonesia Mentawai fault. There are backtrust, and then
You mean
because you didn't mention before, what is possibly contribution from backtrust? It is possible to generate tsunami? Because you talk only megatrust. Most of the talk is related to megatrust, right?
Yes,
Yeah.
yes,
Okay,
yes.
that is
yes.
maybe the question.
Okay, and so I think if we're talking about I think there's a paper talking about maybe the Mentawai fault or Mentawai backtrust fault close to the Pagai Island. Maybe it's more important for Bengkulu. So for that one, I think that they mentioned that fault. They did some research on that one, but I think there's not much data considering how activity of this fault, right? There's no large earthquakes occurs before, and then we don't know, how this fault behavior in the history, and then it's difficult for us to understand what will happen for, whether this fault going to generate earthquakes or tsunamis. So I think maybe for the backtrust in Pagai Island, that needs more research work and to dive down and get more details about how the structure of the fault and the activity of the fault. Until now, I don't know how to quantify that because we don't have much information about this backtrust fault. So maybe it's potentially if we can generate large earthquake, and then potentially that can trigger tsunamis. That's my thought.
Thank you. On Zoom meeting, are there questions? Arya.
Hello, QQ. Hello, QQ.
Hello.
I'm Rio.
Oh, Rio. Nice to see
Hello.
you. I didn't see your photos.
Yeah.
But, where are you? Oh.
I'm fine. And you?
I'm good. I'm looking forward to visit Bengkulu.
Okay. Okay. My question maybe in your slide deformation the around different maybe your slide deformation in Sumatra.
Oh, you want me to show slides?
Yeah.
Okay.
Your slide in.
Hold on. Let me share my slide again, okay?
Yes. Maybe deformation
Which
from
one?
station GPS. QQ.
Which earthquake are you talking about? This one?
Maybe this one.
This one or this one? Which one you refer to?
Maybe yes.
This one?
Yes.
Okay.
The information mapping station GPS. This is effect from the Sumatra Fault or megatrust. The information station GPS maybe minimum error. This is station lies.
Oh, nice.
Yes. Station lies minimum error maybe your effect from the Sumatra Fault or back megatrust, maybe.
Okay, okay. Let me repeat your question, okay? If I was wrong, please let me know. So you want to know the GPS data and lice, whether this deformation come from the megastrust or whether it come from the smartphone fault, right? Is this what you mean?
Yes.
Right, Asha? Right?
Yeah, maybe Rio didn't understand that the live station is moving only one day during the earthquake, right? So, yeah, it's very fair question. You know, he just asked you if possible from Sumatran fault. You know, Sumatran fault.
I think, yeah, if you look at the motions,
It is co-seismic movement.
It's a co-seismic, it's not from Sumatra. Sumatra fault is like, if you're looking at the motions, general is parallel to the fault, right? This is a trenchward motions. So it's like a signal is from the megastrust. For sure, right, Asha?
Okay. One question there.
Does
Arya?
that answer your question?
Hello, Mr. Q.
Hello?
My name is Arya. I want to ask you a question, maybe a little bit. Yes?
Okay, go ahead. Yeah, go ahead.
Okay. So in.
Oh, I see you.
Okay.
Okay, yeah. Go ahead.
Okay. So several days ago, on the national news, BMKG or Geophysical Agency in Indonesia said that there is potential of earthquake with a magnitude of 8.9 with tsunami potential in Bengkulu. So I just want to know your opinion about this news and maybe what is the worst scenario that could happen in Bengkulu if the potential become a real disaster. Thank you.
Okay. I think my short answer is I don't know. But if you're looking at, but I can talk something based on my understanding, okay? So if you're looking at this figure here, can you see my mouse? Can you? Arya, can you see my mouse here?
Yes, sir.
Yeah, okay. So, yeah, if you're looking at, so if you want to know the possibility of future rupture and the tsunami potential, I think it's better to looking at what had happened in history, right? For example, the larger ruptures in 1797 and 1883, and more recently the 2010 and 2007, right? So this part, I think most of the energy maybe is released in last seismic cycles, right? And so with that, I think maybe the potential of large earthquakes, and this where and the tsunami potential is less than this area where further in close to Padang area, right? This area and this part has not ruptured yet, since 1883. So I think this part maybe is more danger than the Bengkulu part because although the 2007 just partially released the accumulated energy, and maybe there's still some possibility for earthquakes, but for large earthquakes that can generate significant tsunami, maybe the possibility is less than this area here in the that's close to the Padang, this area here, because this section is not ruptured yet since 2004 or this series of large ruptures. So that's my answer.
Thank you, Mr. Q.
Thank you. Okay, we are going now. We come last session. Again, please applause for the speaker. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Prof. Q Kian. Halo. A certificate we will send to Prof.
Okay, okay. Thank you so much.
Thank you,
Terima
thank you.
kasih. Terima kasih.
EQ.
Yeah, Asha, no problem.
I will send you email later on. Okay, I'm still busy on this conference.
Okay, don't worry. Take your time.
Okay.
Yeah.
Okay, again, please give a round of applause.
For a excellent presentation from our second invited speaker.
Thank you for Professor Dr. Xu Xiang for the invited speech.
Before we come to the next presentation, we are now in coffee break. Please have your coffee outside this room and please be note the break is only 15 minutes. Enjoy your snack and coffee served. For online, we serve such entertainment. Thank you.
dalam pengembangan Universitas Bengkulu dan kebutuhan akan ilmu dasar untuk memahami berbagai fenomena alam dan solusi penyelesaian permasalahannya, terutama berkaitan dengan posisi Universitas Bengkulu, maka berdirilah FMIPA pada tahun 1999. Pendirian FMIPA diikuti dengan pendirian 4 ilmu dasar, salah satunya ilmu fisika. Jurusan fisika dalam perkembangannya berperan menyelenggarakan tridharma perguruan tinggi, yakni pendidikan, penelitian, dan pengabdian kepada masyarakat. Penyelenggaraan ini tidak terlepas pada kearifan lokal Provinsi Bengkulu dengan kontur berupa pesisir pantai dan pegunungan yang kaya akan sumber daya alam serta berbagai potensi bencana.
Assalamualaikum warahmatullahi wabarakatuh. Hai guys, nama saya Asharam Lubis. Saat sekarang ini sebagai ketua jurusan Fisika FMIPA Universitas Bengkulu. Fisika itu sangat keren, berbicara dari hal-hal yang sangat sederhana, seksama hingga hal-hal yang sangat kritikal, hal-hal yang sangat kompleks. Kemudian fisika itu juga sangat fenomenal. Kenapa fenomenal? Semua sistem di dunia ini dibangun dari kaedah-kaedah hukum-hukum fisika. Oleh karena itu, silakan bergabung. Kita punya peralatan yang bagus, fasilitas yang memadai, dosen yang punya kompetensi, mahasiswanya yang baik-baik. Sekian, terima kasih.
Jurusan Fisika memiliki visi menjadi jurusan yang bereputasi unggul secara akademik dan profesional dalam bidang ilmu fisika di kawasan Asia Tenggara pada tahun 2030. Sejak tahun 2017, jurusan Fisika memiliki 2 prodi, yakni Fisika dan Geofisika, yang berfokus menghasilkan lulusan yang unggul dan berdaya saing. Untuk mewujudkan visinya, jurusan Fisika didukung oleh 16 orang tenaga pengajar yang berkompeten, berkualitas, dan berintegritas. Lebih lanjut, berbagai kerjasama nasional dan internasional telah dilakukan. Kerjasama ini meliputi kerjasama bidang pendidikan, penelitian, dan kelembagaan. Adapun kerjasama yang telah dijalin diantaranya dengan Earth Observatory of Singapore, Nanyang Technological University, Southern University of Science and Technology, China, University Brunei Darussalam, University Science Malaysia, BMKG, dan lain sebagainya.
This is Afroz from University of Brunei Darussalam. I am an assistant professor of structural geology, and I have visited University of Bengkulu last year. So therefore, we have developed this collaboration with Dr. Lubis, and some of his students have visited us, and we were planning that we will visit them also.
Jurusan Fisika juga dilengkapi dengan berbagai fasilitas pendidikan yang memadai seperti perkantoran, ruang dosen, laboratorium yang terdiri dari ruang administrasi laboratorium, laboratorium fisika dasar, laboratorium elektronika, laboratorium komputasi, laboratorium fisika lanjut. taman laboratorium yang merupakan ruang terbuka hijau yang dapat digunakan untuk mencari inspirasi dan tempat diskusi. Ruang kelas, ruang multimedia, ruang seminar, ruang diskusi mahasiswa, perpustakaan universitas, sarana olahraga, serta pusat kegiatan mahasiswa.
Prodi Fisika memiliki fokus untuk menghasilkan lulusan yang unggul dan profesional pada bidang ilmu fisika, khususnya fisika kelautan, geofisika, dan fisika instrumentasi, dan juga menghasilkan lulusan yang mampu menghadapi perubahan baik secara nasional maupun secara global di kawasan Asia Tenggara. Prodi Fisika menyiapkan lulusan yang tidak hanya matang secara teori, namun juga paham secara praktek. Pada Prodi Fisika FMIPA Universitas Bengkulu, mengembangkan 3 bidang minat, yaitu bidang minat fisika kelautan, geofisika, dan fisika instrumentasi.
Untuk menghasilkan lulusan yang unggul dan profesional, Prodi Fisika didukung dengan suasana belajar dan mengajar yang nyaman, pembimbingan mahasiswa yang intensif, dan laboratorium bidang keahlian yang mumpuni. Bidang keahlian geofisika membahas berbagai fenomena kebumian seperti potensi dan eksplorasi sumber daya mineral dan tambang serta kebencanaan. Bidang keahlian ini telah dilengkapi dengan berbagai peralatan yang memadai seperti geofon, magnetotelurik, seismograf 24 channel, resistivity meter multi-channel, proton precession magnetometer, GPS, dan drone. Bidang keahlian oceanografi berfokus pada sifat fisis yang berkaitan dengan kelautan, atmosfer, daratan, dan interaksinya. Posisi Bengkulu yang berada di sepanjang pesisir pantai sangat mendukung untuk pembelajaran serta penelitian berkaitan dengan bidang ini. Bidang keahlian instrumentasi berfokus pada rancang bangun berbagai sistem instrumentasi, otomatisasi, serta inovasi berbagai prototipe alat-alat instrumentasi yang sesuai dengan kearifan lokal dan kebutuhan zaman. Proyek pada bidang ini diantaranya rancang bangun sistem energi terbarukan, otomatisasi, dan sistem instrumentasi lainnya. Dalam menunjang peningkatan kompetensi dan wawasan, mahasiswa dibekali dengan berbagai kegiatan seperti praktek lapangan dan penelitian. Student exchange, magang di berbagai lembaga, dan kegiatan peningkatan skill lainnya. Mahasiswa fisika juga aktif pada berbagai event perlombaan serta kegiatan non-akademik lainnya. Prodi Fisika telah menghasilkan lulusan yang telah bekerja di berbagai
the next
bidang.
session is going to start in 5 minutes. We cordially invite you to be seated. Excellencies, participants, ladies and gentlemen, we would like to invite to the stage our first keynote speaker for today, Dr. Youngsing Swan from Swansea University, United Kingdom. The keynote speech will be moderated by Dr. Nadia Amalia.
Without any further ado,
Please welcome to screen Dr. Youngsing Swan and Dr. Nadia Amalia.
Okay, good morning everyone. Hello from far away United Kingdom. Yeah.
Good morning, Mr. Swan. Firstly, I'll give a brief talk about to introduce yourself first. Yeah. Sorry. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome to the 5th keynote presentation of the 2nd International Conference on Sciences and Applied Sciences 2022. And thank you for staying with us until now. My name is Nadia Amalia, and it is an honor to be moderator for this session. Our keynote speaker is going to be Professor Youngsing Swan from Swansea University. Hopefully I pronounce it correctly, Professor Swan.
Yeah. Very correct. Thank you very much.
Thank you. Good morning. And before we begin, please allow me to deliver a brief profile of Professor Swan. So Professor Swan is an associate professor in the College of Engineering, Swansea University, United Kingdom. He is a civil engineer by training, but at the same time, a hydrometeorologist with a range of interdisciplinary research interests in modeling hydrological processes interfacing with atmosphere and societies. In practical words, he has been working as both a practitioner and a researcher in several fields, including but not limited to hydrology and hydrometeorology using advanced computer modeling, studying extreme events, weather radars, and rainfall nowcasting, flood risk management, and climate change impact adaptation in water sector. Now, moving along to our session, if anyone has any question to Professor Swan during his presentation, you may write your question on the chat box or by raising your hand after Professor Swan finishes his talk. Please give a warm welcome to Professor Swan. And Professor Swan will be speaking to us on the quantitative modeling of hydroclimatic extremes. Professor Swan, you will have about 40 minutes, including question and answer session. The floor is yours.
Okay, thank you very much, Nadia. And once again, hello from United Kingdom. I know it's quite far away. One of the things, I just watched the fantastic promotion video you demonstrated. I wish I could be there this morning in person. Due to the COVID restrictions, I couldn't travel. But again, so the background for my talk, actually, I was asked by my colleague, Professor Dominic Reeve, for kind of replacement for him back in summer. So I think I may give it a go because I've been involved in a project with some Indonesian partners. Actually, before the COVID, I had a chance to visit ITB in Jakarta. We had a joint project supported by the UK government on the kind of compound flooding, which I will cover a little bit later on about this kind of event. So it gave me a good impression and very impressive, this collaboration. So I've never been to Bengkulu myself, but from what I've learned, your video is a fantastic place, a beautiful scene, and your beautiful campus, a good student. The other thing I would like to give a warning is this very early morning now here, so the first time for me to give such a talk around 3 or 4 a.m. in the morning. I feel a little bit, if I behave something strangely, a little bit disoriented, in the morning. So in the meantime, I now quite understand why some of my students, they couldn't turn up for my early morning lectures, etc. Okay, without further ado, let me start by sharing my screen, share my presentation. Just double check. Can you all see my screen now? Yeah. Great. So let me get started. Well, once again, the background of my talk, actually, I have got a few more different, presentation, different areas, because I wasn't quite sure, the audience and the coverage, before I came to this sort of conference. So I picked up something I thought might be closest to the topic of this conference, which kind of talking about this hydroclimatic dreams, probability theory, etc. But indeed, as Nadia mentioned, I had some experience in different disciplines, different areas, but particularly in flood risk management. So today my talk is going to be going through a few components. I have to say the talk is partly produced by my former PhD student, Dr. Han Wang, who now works in China, quite busy at the moment. So she graduated last year. So the content of my talk today is a little bit of background, why and how we did this, and talking about the quantification of hydroclimatic dream in general. And I will demonstrate some of the toolbox we have produced recently in supporting our research in doing this, dream studies. And also some of the practices we have done so far on decision making on extreme events. And finally, a list of publications we have produced in the last couple of years, which I hopefully will be interest of some of your audiences. I believe this of the topic have been covered before I joined in this conference this morning about climate change. Although tsunami or earthquake, I understand, is also associated with this change in climate, but probably tsunami is more close to have this kind of closer relationship with the climate change impact. For me, as I mentioned, my background is about flooding, hydrology, hydrometeorology. So we look at more closely at the sort of rainfall, these surface and coastal flooding, that side. But in general, we all have seen that recent years increase this kind of more extreme around the world. Not only just flooding, as we normally talk about, and the tsunami, of course, the storm surge, etc., but also, especially this year, if you have watched news on TV, you would have realized that the heat wave now become another hot topic, right? Especially in Europe, where we don't have air conditioning as you do in Indonesia. So it was quite hot summer for me this year. Well, we enjoyed summer, but the heat wave caused huge problem here as well. Of course, this ash sheet melting in polar regions caused sea level rise, etc. So, generally speaking, now the tool we have in hand to estimate or even further predict this kind of risk associated with climate change impact is we still use, unfortunately, I have to say, the traditional this paradigm. We see fundamentally this risk is associated with a certain level of probability, where that probability of this event happening is more or less static or stationary. So this is something I will mention again later on to see why this is a problem for us. And so current simulation of climate projection models still involve significant uncertainties. I believe this topic has been covered by other speakers as well. So although we now have quite high resolution, for example, in my area, we can now have as high as a few kilometers this resolution in space for climate simulations. We still have large amount of uncertainty in model in prediction. So we can't say for sure what exactly going to be happening, not just in a few years, even if you go straight around this direction for a few weeks ahead, there's a large amount of uncertainty coming in. So that's another big issue as well. So recently, I would say more and more this kind of data set become available, which is also a very positive movement. I still remember back 20 years ago, we were struggling with, with opportunities, so to say, getting enough data support. But nowadays, you can find also the information and the simulation result from around the world, from different data centers, and again, with a high resolution. But on the other hand, we don't have so-called sufficiently developed tools to deal with kind of data processing, especially with regard to the extracting of this useful information, etc. Well, that's probably too much to cover the background, but I will say this. So the topic today again is about hydroclimatic extremes, right? So I will go through the few things we have been doing recently, but the key point I want to make is, again, traditionally we talk about the risk associated with climate change impact. One of the common practice, because I have engineering background, so if we talk about something happening, probably I think in your discipline, some of your audience is talking about an earthquake. You apply the similar sort of concept called return period. That is keyword in our sort of civil engineering discipline, talking about the flood risk management, talking about the flood defense structures, talking about super flood. So the chance of the super flood happening in terms of probability. So we use the return period as a standard approach. So in our mind setting, the return period appeared to be a static, a stationary value. So we talk about something can happen once in 10 years, 100 years, etc. But we are now being challenged by the new normal, so to say, the climate change impact. We do understand climate is changing. We have experienced, this increase of this kind of occurrences of, super flood, heat wave, etc. You can see clearly there's conflict or clash between our traditional belief or assumption and the new normal. So what can be done to increase our understanding, to better bridge this gap, so to say, to further quantify more accurately this probability and their development or variation in the near future regarding to the probability of this kind of hydroclimatic extreme. So that is the key point I want to highlight. So that is why we developed so-called non-stationary framework and risk associated with a new concept of risk. So again, the other direction is regarding the climate change impact, about flooding, we normally deal with not just one single driver. By saying one single driver, I mean most of the time we're talking about extreme rainfall, which may cause flooding and landslides, of course. But also, if you look closely at the coastal region, I believe this is also the case in many areas in Indonesia, where we have experienced this kind of compound flooding. So one driver is rainfall, the other driver is from the sea, is storm surge. So that's the complex issue. So what's the joint probability of the two drivers, sometimes even three drivers? And now we can talk about the joint probability of earthquake, which can cause tsunami, which further cause storm surge, plus rainfall. So it's multiple driver, and this is something we need to think about. So one of the first efforts before we even went further to to this study, we look at the rainfall data set itself. So the example shown here is about the coverage of Great Britain and Northern Ireland. So we pick up the main study area is this is called the United Kingdom, Great Britain, and Northern Ireland. But this part, the main part, we call it Great Britain, where we have In the north, we have Scotland, and to the east, we have England, and this is where Swan is based, somewhere here in Wales, or the three countries. So the challenge we wanted to address is this large amount of data. How can we generate statistics and further trend analysis from using this large amount of data now, which has become more and more available over the recent years? Because it's clearly associated with our target about hydroclimatic dream, varying with with space and time. So we call this from data side, it shares a common feature called grid base, right? So we developed a new this sampling method, trying to pick up this kind of this data set in a random manner, and we further look at different aggregation. So the shape constraint sampling method. We look at catchment based, area based, sometimes even political boundary based sampling method, so that we can generate corresponding statistics. For example, a river catchment, a city, or sometimes even province, and to look at the variation over time about this extreme. And then the next step we developed is to apply a new concept, a non-stationary framework, to quantify climate impact on extreme events. I have to say most of you should have been aware of this kind of in general mathematics about this probability theory. Traditionally, we see this as stationary, where you see this commonly used GEV distribution, which has 3 parameters. There's no mentioning with regard to time. So this is one of the representation of that GEV function, distribution function. You can see here, you normally have to deal with 3 parameters about standard deviation, about the mean value, and about the shape value of the distribution. So the common procedure is to simply to get sample data to estimate these 3 parameters. Of course, this has become quite mature nowadays, and you can easily pick up some algorithm from using MATLAB, for example, to quickly fit, so to say, this kind of distribution. But it has a fundamental problem here. When we talk about climate change, we talk about the time. So how can we include that kind of dimension or timing dimension into this representation? Therefore, we include the so-called non-stationary perspective, and we see or we set these parameters as time varying. You can see here we give a new subscript about time t here, which means all these parameters are going to be dependent on time, not just a single fixed value or optimized best value you can fit, but also it depends on time. Therefore, we could go further to study this variation of the distribution over time. This is some initial idea. And one associated study we did was to look at another country, this large data set for Australia over the last century, about 100 years. We look at this annual maximum daily rainfall, which look at extreme rainfall for this country together with Great Britain. So by applying the sampling method, a toolbox we developed, we could generate a larger data size so that we can look at this distribution of this extreme value over space. You can see here is the distribution of this extreme rainfall over space. We further quantify this distribution using another model, the generalized linear model, GLM, to give a representation of the distribution of these parameters for Australia as well as Great Britain. So these are some of the results which has been published in one of our papers last year also about the comparison among these kind of different models. We try different models. One is a stationary model, the other non-stationary model. And with regard to non-stationary model and stationary model, the big challenge is you have to fit best value of the parameters. So there are several choices. For example, you can use maximum this kind of linearized movement measures, we also applied the Bayesian Monte Carlo simulation to identify bias parameters and to see the performance. One of the striking, let me zoom out this a little bit, talk about this trend. So we initially look at the trend associated with climate change. This is TOR, which is the Mann-Kendall test trend analysis, and this shows a clear picture or a complex picture, I would say, with regard to trend. Everybody had talked about the recent change in the extreme rainfall, but it's not always the case. If you look down to the earth, it's not everywhere had an increasing trend. Sometimes you may have even decrease. But generally speaking, for Great Britain, here we have a strong trend to the west coast of Scotland. You see here, very this yellowish and even reddish color. But on the other hand, some small areas within Scotland and in northern country and the corner of England, you see sometimes even decreased trend here as well. And it's also more interesting to look at Australia, where you see increase. Well, in this region, I have to say I was not quite sure whether this is correct or not, because we all understand in this region is a remote and desert area, but still we see the increase of the rainfall. Although it's certainly not extreme, but we do see an increase of extreme rainfall in terms of kind of extreme rainfall in that region. But if you move to the east coast line, they remain more or less unchanged. So over the last 100 years. So this is one of the things we observe. And this is further results associated with that study. We use GILM model to further quantify the distribution so that we can have a clear picture about the distribution of these three parameters. Right? And in Australia, again, we see the big increase of this mu value of that parameter value, which means, in general speaking, the average so-called extreme is not so extreme. The average extreme, say, every other year, this is the probability value going to be changing in the coastal area, but in the large area in Midland, it's not quite clear. So, but spatial variation, I have to say, is not our main interest. Our main interest is to look at the climate change impact. So therefore, we look at another dimension, the time dimension, to look at how this kind of climate change impact has had some contribution towards the variation in time of this extreme rainfall values in Great Britain. So this is our result that we look at two parameters. So again, you can look at the mu parameter. The mu parameter represents again the normal extreme event. Once again, this picture is more or less a mixture of both directions. You can have increase and decrease, but generally speaking, the increase has get more occurrences around the country. But still, you have some decrease. So once again, showing this heterogeneity among these parameters. And we went further to look at compound event. This is something I mentioned earlier. Look at the different drivers, rainfall, storm surge, etc. So for that matter, we apply this so-called time-varying parameters to a very common sort technique, copular construction. Use a copula to represent link this kind of multiple driver probability distribution. And one study area, we collaborate with several institutions in Southeast Asia, in Vietnam actually, in Ho Chi Minh City. I'm going to be traveling to Vietnam next week, and so to see some of the friends there. But this is another, so this case study we did together in Ho Chi Minh City. The city had been experiencing huge problem in, the surface flooding. basically there are two threats. One is come from land. So the large area of the Ho Chi Minh City, which is kind of capital, economic capital of Vietnam recently, and quite a popular place, a lot of population there. And we have seen the surface flooding over the years. And from the sea, another threat is storm surge, the wave, etc. So they are facing a joint threat at some point. So if there was a kind of large amount of rainfall, and in the meantime you're facing this storm surge, as whole city can be a big problem. So we look at how likely climate change had an impact on the increase or either decrease or increase of this kind of joint probability event, compound event. So we try to model that. And this is some part of the results. We fit the copula, look at the variation of the copula, there are parameters associated with different return level, return period. For example, 1 in 10 years, 1 in 2 years, 1 in 100 years. And you can see here clearly the parameter has a different profile here. I can't go into detail to talk about this curve, but generally speaking, this shows a shift of that parameter and a different scenario. And after we generate this kind of copula model, we then apply this model to kind of bootstrapping to generate samples to drive further so-called 2D model, telemark, to simulate the kind of consequence of this change in climate. These are the comparison among these simulations in dry season and wet season. I have to say, most of the area doesn't seem to have very clear, difference between the climate change now and in 50 years. However, we do observe some of the area. For example, the non-stationary, the model showed an increase in this area to the east part of the city and somewhere here as well. Indeed, we observe this kind of change in space with regards to the climate change impact on the joint, so the compound event. So the conclusion we draw were traditional and stationary conditions significantly underestimate the compound flood in Ho Chi Minh City. However, by applying this kind of non-stationary framework, we were able to simulate this more accurately, this consequence of this climate change impact. And that had been published in the World Resources Research earlier this year, together with some partners in Netherlands as well. So the other, I would say, the third part of the talk is slightly different. We talk about this kind of data set once again, but this time we think about sampling, and our intention was to support the further study using machine learning, artificial intelligence, trying to quantify some features and to further examine how these features can change over time due to climate change. That was our initial intention. In order to do that, we again refine our toolbox. We design a kind of SPER, the toolbox, special pattern extraction and recognition toolbox, to apply the toolbox in our study area. This is one of the applications of this toolbox, showing this catchment-based rainfall, extreme rainfall extraction and quantification. Once again, we try to see how the probability parameters vary over different features of the catchment. For example, for a small catchment or even larger catchment, you have different special features. First of all, of course, the area. The second is the orientation. And thirdly, you may have a round shape of the catchment or quite a narrow shape. So they may affect that distribution of extreme event. So that is the first application. Second application, we try to quantify the most commonly appeared this kind of extreme event, how the distribution look like. I mean, the rainfall system look like over the last 100 years. And you can imagine that's going to be a tedious work if you do it manually. But with the help of this computer toolbox, we were able to generate, to analyze this appearance with different spatial coverage, different location, different intensity of this rainfall system. In the end, that toolbox helped us to identify there's some common features of the rainfall system in England, in Wales, and in Scotland. Why is this useful? Because we are able to use this information to further check our engineering design, which area is more susceptible to this kind of extreme event, and where is the most common place you are expecting to see this sort of extreme event. So that is very crucial as well. So this is application 2. Application 3 is something associated with my other research direction, which is weather radar, and Nadia just mentioned. And the weather radar is one of my case study areas as well. For weather radar, we are more interested in the movement of extreme weather system, here the rainfall system. So how can we track and further predict the route of extreme rainfall system? For example, this is one of the studies we did together with some Chinese partner in Guangdong in southern China. We used weather radar through the data site to track one extreme event happened in 2019 and to see the variation in space, the track intensity of the rainfall system. So we follow up this approach to further apply this toolbox to help our study in application of machine learning or artificial intelligence to predict this kind of pattern-based change in future. So this is a kind of continuation from my previous slides, which shows you most commonly featured this kind of rainfall system happening in the UK. Now the question is, so are these features going to be changing on climate change? If so, how can we identify the change of these features? So we have to train our neural network. In this case, we use CNN to pick up these patterns and then to model this, to link the change of the pattern with some driving factor as well. So it's still a kind of ongoing study of the research after Han graduated. So I'm quite interested to push forward this kind of study. But the current outcomes showed quite promising outcome. We were able to generate the CNN neural network to represent, even predict this sort of feature of extreme rainfall system. And finally, if I may, it's kind of another study area which had been linked to this kind of motivation recently, is about what can be done if we do see the change in climate and correspondingly we do see the increase of flood risk in certain area, and what can be done in terms of decision making. So decision making is the more complex issue. We traditionally look at mainly at the engineering side, the science side, without realizing actually we are heavily relying on human decision. And how can we model reaction from a human is another challenge issue. So this is why we developed, look into the human reaction towards decision making after they received our forecast, for example, our prediction or early warning, what can be done, what will be done by human beings, given the condition that they are entitled to do certain actions and they are facing certain consequences as well, associated with different decisions. So we developed a mathematical model called cumulative prospect theory and data-driven two model altogether, and to see how this interaction can be modeled. And we further verify this by using case studies in Netherlands. This again is ongoing research work and going to be published soon, I would say later this year, about this kind of mathematical modeling of decision making, specifically focusing on the dream event and flood forecasting and early warning. And finally, this some of the selected related publications which we have produced over the last couple of years. I hope this from the top very quickly, if that's interest to some of your audiences. If you want to know more in this area, please get in touch. And but once again, this is being prepared without knowledge about the audience of this conference. I hope this kind of helpful, but do please let me know if you have any questions in this area. Thank you very much. Thanks for your attention. And any questions?
Thank you very much, Professor Swan, for addressing this interesting topic, in particular with the current development of AI and the application. And if anyone has any question to Prof. Swan, you may write your question on the chat box or just raise your hand for whether for offline and online participants to directly talk to Professor Swan. Is there any question, maybe from offline participants?
Hello.
Yeah.
Thank you, moderator.
Okay.
My name is
Please.
Harlubis from University of
Please,
Bengkulu.
Harlubis.
Yeah, I
Hello,
have.
I see you.
Yeah, question, Prof. King. Now, as we know, Indonesia is very popular to meteorological hazard. You know, hydrometeorology hazard. We know during the dry season, we have extremely drought, following sometime by forest fire. And then during the wet season, we also have extremely flooding, landslide, and then as well as coastal erosion. You already saw, I think, very fantastic model, especially for extremely rain precipitation. So my question is, how accurate your model compared to the situation already happened? For example, you saw in Australia, even in England. And then, what do you think is the effect of the size or this discretization of your model? Because you didn't show whether this affect your uncertainties of the model, or because you know the prediction is very important. So that's why the model should be accurate as much as possible, right? That is actually is really nice talk. So I'm just wondering if you could explain more. Thank you, Prof.
Thank you very much. That's a very good question, actually. Excuse me. That is one of my question to my student every time I saw them, showing the modeling results. So one question I would like to ask: are you confident about your model result? How can you verify your model good enough to to get this prediction right? So yeah, that's a very good question. So I think in terms of probability, this modeling it's been a challenge. It's not unlike the physically based model. So I've been doing this modeling work, not this kind of non-stationary probability model, but this kind of physical model, like weather prediction, like flood prediction, flood simulation. So for that kind of data plane, I would say, I'm sure you all know that we have to follow the model calibration, model verification, and validation, this approach to increase our confidence before we can even apply our prediction to support further decision making, right? So we have to have very good so-called indexes, statistics out of your model prediction compared with the observation. That has been done traditionally in this kind of physical models, including hydrologic model, hydrodynamic models, and storm surge model, etc., etc. But things become more tricky when we talk about the probability model. So you can never sort of verify how accurate the model is. So what can be guaranteed is when you develop a new statistical model or probability model, you have to, apply your model to the historical data set. So by doing so, you are effectively following that fitting procedure. This is why I say with a fit model, not to build a model. So this is a clear difference between the statistical model or probability model and the physically based model. But after this, we can use like some technique like bootstrapping technique to further validate our model. So I haven't shown these results there in my slide, but certainly that has been checked. But even though I agree with you that we are not so confident when we talk about climate change, and not because our model is not good enough. It's really because that our understanding are still quite limited in view of climate change impact. So that is my understanding. But currently, for all the statistical model, the probability model, the only thing we can do is we have to verify our model against historical data set. You have to look at how these dots are closer put on your fit the curve. So that's to be simple. It's just like that. Of course, there are going to be some certain metrics you have to show how likely the uncertainty going to be. But again, we are facing challenge. And the other issue associated with this application of the prediction is one thing I did not mention in my slide because of the time limit. I always say this, when you use the climate projection, there's something associated with climate projection, you have to keep in mind the climate projection is not a prediction or not a forecast. Although it seems like it is forecast or prediction, but in fact it is not. Okay? It's just like a what-if analysis. You give a certain condition, this is going to be one of the realization of future climate. It may or may not even happen in future. But unfortunately, I see so many research, so many publications, they just use the climate projection and further drive the downstream model, say, okay, this is going to be a climate change impact. But keep in mind, this is just one of the possibilities of climate change impact, the consequence. They may or may not even happen. It's certainly not a prediction. This looks like just like the if analysis. Again, this further complicate this issue, this climate change impact study. So the thing we have been doing, we try to see to a large extent, so how likely this sort of event going to be changing. So it's still a long way forward to further bridge this probability to the downstream application. Say, okay, this is going to be the changing in the dry climate, in the wet climate. It's still a long way to go. But at least we can see how likely the change will be happening. Because by looking around, we used to rely on the kind of stationary model. We wouldn't be able to even estimate the change of probability because that sort of minus setting does not allow us to even consider these changing, factors into this probability. So that is, I hope I answered your question. Right.
Okay, thank you.
Do you have any further question, maybe, Pak Lubis? Was that enough? Okay, I think that answer Pak Lubis' question. Maybe any question from online participants? And from offline participants also? I myself do have a question, Prof. Swan. So,
Please.
yeah, thank you. So, from what I get from your presentation, you mentioned that you and your team also developed an AI for the research, and so does that mean that you and your team developed the program itself? And I just need you to elaborate about it more. Yeah.
Sure. Yes, the AI application is a big topic. I'm sure everyone knows about that, especially recently. Everybody talks about AI application in their own data plans. And with regard to this kind of research area, I think this is CNN or there's existing the software package all around, so it can pick up the software package, Python, etc. But the big problem is, again, if you look at this application in this large data size, the big challenge there is how you can apply this existing algorithm, for example, CNN or any other training method, to our large data size. If you think about the size of the data size I mentioned, it's a daily rainfall, and the spatial resolution is somewhere around 1 square kilometers. For a small country like UK, you have even one day that data. So every day you have like a picture, and that picture is a gigabyte level, and that's just one day. And you got 360 days in climate model output, and then further you got 100 years. To think about this large amount of data size is a really big challenge by applying any training model altogether. So that background. So the contribution we have made is try to simplify this process by streamlining the sampling method, and we can further process the data to link this kind of data set to the different algorithm. And for that particular example I've shown, so our intention was to firstly to look at the large data set to quickly generate the most likely list of the features, and then this is only the first step. We build a CNN model which can model the large data set to say, okay, this is going to be the feature. We extracted the pattern extracted from the large data set. So the next, we can apply the CNN model to climate projection. So you get another 100 years of prediction or projection, and you can track the same amount of images as well as the features, pattern. And then you can compare how patterns would be changing against historical or baseline observation. The second part has not been achieved yet. So I have to say we are trying hard to move towards that bit. So yes, we have developed a certain amount of the code base by ourselves, so by applying. So that toolbox is freely available on GitHub. So anyone interested, I can pass a link to you. And also in my publication, so there are always a link about the GitHub. So that's a repository of our code. So they are all freely available.
Thank you very much for the response, Professor Swan. And it seems that there is no other question for now, and maybe participants can further mention any question to Prof. Swan after this session, if there is any other question. Yeah. Thank you very much, Prof. Swan. So
a pleasure.
Thank you very much. So, and apparently we have finally come to an end of our session. Thank you very much, Prof. Swan, for addressing the interesting topic in the early morning of UK time. Thank you very much.
I'm already getting you. I'm going to have a coffee.
We would like to kindly present Professor Yun Sim Swan with an appreciation certificate, and I request, here we go.
Oh, that's amazing. Thank you so much.
Thank you for the committee, and please the committee to take a screenshot of Prof. Swan and the appreciation certificate in 3, 2, 1. Okay. All right. Again, Professor Swan, thank you for joining with us today, and please all give our warmest applause for Professor Swan. Okay. Well, thank you very much.
Thank you, everyone. Much appreciated for this opportunity. Thank to Asha as well for initial connection. So I'm looking forward to further collaboration, if possible, with any of our academics there in Indonesia.
Okay, thank you, Professor. It's nice, challenging for us in the future to start collaboration. We have in Bengkulu various, very beautiful beats, but on the other hand also, Okay.
I have had a collaboration with the ITB team there with kind of inland flooding. You must have known them quite well, and also saw the places I visited in Jakarta in your video. So it's reminded me it was a nice, very nice country experience I had before COVID. Unfortunately, I couldn't go afterwards in the last 2 years. All right.
Anyway, thank you so much for joining us in this beautiful conference.
Thank you very much, Prof. Swan. And also thank you all to the participants. So I give back the session to our Master of Ceremony.
Okay. Thank you.
What an excellent presentation from our first keynote speaker.
Thank you for Dr. Yun Sing Swan for the keynote speech.
Excellencies, participants, ladies and gentlemen, we would like to invite to the stage our last invited speaker for today, Professor Dr. Sri Widawati Cahyarini from National Research and Innovation Agency, Indonesia. The invited speech will be moderated by Mr. Budi Harlianto, MSc.
Without any further ado,
please welcome to the screen Professor Dr. Sri Widawati Cahyarini and Budi Harlianto, MSc.
Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone. I'm Budi Harlianto as moderator for this session. This session the last of ICSAP 2021. The speaker at the session is Professor Sri Widawati Cahyarini. She is from the National Research and Innovation Agency, or BRIN. Our speaker this time is a geology expert with undergraduate and master degree at ITB and postgraduate at Germany. Professor Sri Widawati will give a presentation about colors as climate archives records from Indonesia. This session will be invited to part one is presentation by speaker from 30 minutes, and part 2 question and answer session. Ladies and gentlemen, we invite our speaker to the session, Professor Sri Widiawati. Time for you.
Thank you for the moderator. So should I share screen? Yeah. Okay. Good afternoon, everyone here. So thank you for the opportunity to present our work in this international conference. So I'm here today to present the coral as the climate archive, and also some result of our study from the Indonesian coral. So as the introduction, that why Indonesia is very important for the climate study. So because it's located in the two basins, it's Indian Ocean and the Pacific Ocean, and also the two continents, Asia and Australia, and which generate the influence of the regional climate in Indonesia. That is monsoon, and also Indonesian true flow, and also this interannual and two-annual phenomenon in the Indian Ocean, and also in the Pacific, what's so-called IOD and so. And this the Australian monsoon that influence the regional climate in Indonesia is characterized by the changes in the wind direction that modulate the rainfall over Indonesia. And during northwest monsoon, when the winds blow from the north to the south, southeast, and will bring the wet monsoon in Indonesia. And oppositely, during the southeast monsoon, and Indonesia will get dry seasons. The dominant wind just blows from the Australian continent to the from the southeast to the Indonesian region. And this also influence for the ocean circulation here, when during the northwest monsoon, the fresher water from the South China Sea will goes into Indonesian Sea, and then oppositely during the southeast monsoon, is the fresh water goes back to the South China Sea. That will modulate the salinity across Indonesian Sea. And this is the Indonesian true flow exit passage that is the water mass transport from the Pacific, which is warm and dense, to the Indian Ocean via the Indonesian Sea. This also modulates the regional climate in Indonesia. This figure shows the salinity which is modulated by this the IPF, that as I explained before, that during the northwest monsoon, the flow goes from the South China Sea goes to the Indonesian Sea, and so on. And this is the interannual to annual climate phenomena, such as El Nino Southern Oscillation and Indian Ocean Dipole. And so our IOD changes the rainfall variation in the Indonesian Sea. In the normal conditions, and we can see that the Walker circulation, that is the movement of the air masses in the west-east zonal direction. The trigger for this movement is the
air pressure around the equator above the Indonesia, which is relatively warm, so its density here is low. And then the local circulation drive the trade wind from the eastern to the west Pacific. When there is the El Nino, then the sea surface over the western Pacific Ocean is cooler than usual. And then the SST anomaly is positive or warmer in the eastern Pacific, and the negative anomaly in the western Pacific. The impact will be high rainfall in the eastern Pacific and then dry in the western Pacific. And oppositely, it happened during the La Nina. And there is also this similar phenomenon in the Indian Ocean, which is called as Indian Ocean Dipole, which is characterized when the SST are warmer in the tropical Indian Ocean than in the West Indian Ocean, and more rainfall across the Eastern Indian Ocean, and that's we call as the negative dipole mode. And then oppositely, it's happened which called as positive dipole modes, and this is influence the rainfall for the Indonesian region. And one indication of the effect of this phenomenon and on the climate variability in Indonesia is seen from the SST sea surface temperature data, and this slide shows a composite map of the SST anomaly during IOD event, and this is in the left panel is positive IOD, and the right panel is the negative IOD SST anomaly composite, and in upper is extreme event, and then the lower is moderate event. On this map, we can see that during the positive IOD, there is extreme cooling more than 1 degree Celsius in the southwest Indonesia, and in contrast with when there is extreme negative IOD, there is a warming that's higher than the 1 degree Celsius. And this is a composite map of the SST anomaly during the ENSO event. And on this map, we can see also that during the strong El Nino, the southwest part of the Indonesia is cool more than 1 degree Celsius, whereas during La Nina, it warm up to more than 1 degree Celsius. And in the moderate or weak, and the SST anomaly is around minus 0.4 degree, which is less than 1 degree Celsius, while in a moderate or weak La Nina, the SST anomaly is also less than 1 degree. So then, how did the coral record the SST variability and its respond to the IOD or the ENSO? Here is the coral type that we use, that usually we use in the coral paleoclimate study. This Porites, Endiploria, and also Montastria. And this the appearance in the nature, and then this is the X-ray from the Porites slab, and this we can see the photos of the polyps of the Porites, Diploria, and the Montastria. And I myself usually use the Porites coral. And here is how we take the sample, and there are two methods. Underwater collecting sample, we use the pneumatic coral coring, and then this for on-land coral, we use hand coring, which is usually used from the for the road development, something like that. And then we use usually to collect the fossil or soft fossil or dead coral on land. And here, after we, especially for the collecting the modern coral, after collecting, we cover the hole with the concrete, or we can use also some dead coral to cover this the hole. So then there will be no organism enter this hole. And this is coral core that we collecting, and this the equipment that we use to for underwater coring. And the laboratory method, we use the ICPOS for coral strontium calcium analysis, and gas band for the delta 18O, and this is the radiograph or Ronson of coral skeleton. And here we can see the clearly annual bending of the coral. This is the Poritas coral, so that's for one yearly annual growth. It's represent for dark and light band. So we can develop a chronology from this density band, and we for the corals subsampling we use for the geochemical analysis. Then we usually sample along the growth axis. And this is the proxy. There are several proxy that we can measure in the coral. For example, this oxygen isotope. We can use for, some people also use for the SST reconstruction, and also, but usually we use for the seawater isotope composition. And carbon isotope we use for the photosynthesis reconstruction, and also we can reconstruct for the SST from the strontium calcium, and also from the ratio uranium calcium, and etc. And the commonly used proxy in the coral is the ratio of strontium calcium and also delta 18O. And as we know that the relative variation of the coral delta 18O and strontium calcium are governed by the thermodynamic principles, and the ratio of 18O to the 16O in coral aragonite is depend on the ratio of the 18O to the 16 in the seawater, and on the equilibrium constant. And similarly, the incorporation of the strontium ion in the coral aragonite, which is substitute for calcium, depend on the the ratio of strontium calcium in seawater, and the equilibrium constant. So for both proxy, this coefficient distribution is temperature dependent, and the temperature dependent is known from the laboratory experiment. So then for the oxygen isotope composition of seawater is influenced by the freshwater flux, and mainly this rainfall. So that, and then in contrast, that the strontium calcium ratio of the seawater is constant over the calibration period. So then strontium calcium is we assume that is showing the temperature proxy.
So here there's some record from Indonesia that here we can see that this is the modern or living coral record from Enggano. And here we can see that the September, November mean SST anomaly during the extreme positive event of the 2006, 1997, and 1994 from the OESST, and then also SODA dataset, and also the SST product from the ERSST, and the positive IOD even displays strong difference with the extreme even dominated by the westward extend strong cold anomaly along the equator, and with the weakened cooling to the region of the Java and the Sumatra. Here you can see here. And this right panel is the monthly coral strontium calcium record from the two colony, and then this is the second one is SST estimate from the Enggano coral strontium calcium, and this is the uncertainty that's estimate from the Monte Carlo approach. And here we can see that the positive IOD even is clearly also recorded in the coral from the Enggano. And this is the scatter plot ABC. This is the scatter plot, and this is the time series data and the histogram of the September to November SST from the several SST product, including the Enggano, this from the coral. And then here we can see that the September, November Enggano SST are highly skewed toward negative, and then followed by the SODA, and then also had this SST that are moderately skewed, and while the ERST we can see here that's is close to the symmetric. And then this is the time series of the Manley Enggano ST from the coral and also from the several data set. And this is the histogram of this the SST is coral SST, and also the data set from the several data set. And here we can see that the difference between the coral SST and ARSST and also HADIS are statistically significant during the strongest extreme positive. The IOD even is from the 1961, 1962, and also 1961, and here 1994, and then 1997. And so the results from the Enggano, that from the modern coral, we can say that the coral reconstruction of the IODA is SST can provide the magnitude of the extreme positive IOD event, and in combination with the SST reanalysis product improve our understanding of their variability. And the uncertainty of the SST reconstruction based on the coral strontium calcium ratio should be reduced by developing further replication core from the IOD East region, and then or by improving proxy calibration of the strontium calcium and SST relationship. And the coral proxy data likely provide the best estimate of the IOD variability on the historical and millennial time scale. And this is the second is the record from the Timor coral, and here's the Timor coral proxy coral data 18O, and then this is the SST reconstruction from the strontium calcium, and here this reconstructed data 18O seawater from the coral. And here we compare the observe the SST from Ombay and coral strontium calcium, and we can see that coral strontium calcium is well correlated with the measured SST at Ombay. And here is strontium calcium is convincing as the SST proxy, which is shown in the spatial correlation between monthly SST and this is the spatial correlation between the SST from Timor and the global SST, and this is the coral strontium calcium with the global SST, and then this is spatial correlation from the coral delta 18O with the SST. Here we can see that the improvement is capturing that the strontium calcium alone is so well represent the SST rather than delta 18O. And this is the interannual bandpass coral based SST and salinity, and this we compare with the Nino index, and below is below is we compare with the DME for the IOD index. So then we can see that the coral SST is correlated well with the ENSO, but for the IOD, it's correlated with the SST and the salinity. And here is the spatial correlation of the salinity and SST with the Nino index and the IOD index. So from the Timor, we can say that the coral strontium calcium based SST, and then also delta 18O seawater based salinity record capturing the strong seasonal cycle at Timor, and then the utility of the coral strontium calcium thermometer improve the SST reconstruction, then using coral delta 18O only. And on the interannual time scale, coral based Timor SST and salinity are sensitive to the Indian Ocean dipole, whereas the ENSO only the influence SST but not salinity based on coral Timor record. And this is our study on that coral, which is dated for covering the medieval period, which was 1,100 to 1,140, and this is the usually one when we study the dead coral, then we should also calibrate with the modern coral first before we go to the fossil coral record. So here, because our fossil coral is around Lampung Bay, and we have how can I say, that we have the modern record from the Enganos. So first we have to look at the Lampung Bay oceanographic setting is not so significantly different with the Engano. So then we can use the Engano modern record as the as a comparison for the dead coral from the Lampung Bay. What I mean is we can compare we can compare the record from both sides. Here we can see that this both SST from the Enggano and then from Lampung Bay is good correlated. So then we can use the Enggano modern coral for the as the comparison for the dead coral in Lampung Bay. And this is the strontium calcium content in modern coral sample, and then in the subfossil in the monthly resolution, where one data represent one month. So then here we can see this 1 year is one sinusoid. So the top panel is the result of the coral strontium calcium measurement, and the bottom panel is the anomaly of the coral strontium calcium. Here we can so in the modern Enggano, it can be seen that there were only clearly two extreme anomaly signal of the strontium calcium, and then which is coincide with the IOD or the El Nino, while in the medieval coral we only see one extreme, see here. And so this so much more clearly that this is the comparison of the living coral in Enggano and then the dead coral from the strontium calcium from Lampung Bay, and this is the index of the El Nino, and this IUD index, and this the temperature from the region IOD is southwest Sumatra. So this and this is the SST anomaly. Here we can see clearly that there are this extreme. We suppose that this extreme even of the interannual or annual IOD, like in the dead coral strontium calcium. And if we compare the seasonality of the dead coral and then also the with the modern living coral, we can see that there is the seasonality of the dead coral, the strontium calcium content in the dead coral is lower compared to the modern coral. And here we compare from various proxy from Indonesia, and we can see clearly from the this is from the marine sediment SSD reconstruction, and then this from the lake sediment reconstruction. And we can here we can see that for the temperature is increasing temperature, and this our coral is only cover a short time period. And to highlight the medieval period, here we compare the record from coral from coral from Lampung Bay and another record from the Mentawai. Then here we can see that this is the coral proxy anomaly from the Lampung Bay, and this is from the Mentawai. And here we do the interannual annual band pass filter. So then we can see that during the medieval we can indicate the SST anomaly. It's here we can in our record is one SST anomaly, and here from Mentawai record we can see some interannual phenomena. And so this from the medieval coral proxy we can say that the modern coral show larger interannual variability than the medieval coral, and the frequency of the interannual climate phenomenon occurrence is higher at the present time than in the medieval period. And the seasonal cycle of the medieval coral is reduced about 50%, and the skewness of the strontium calcium data is lower. And so it's as the take-home message that the coral strontium calcium is convincing as the ST proxy, and then coral oxygen delta 18O alone cannot be used as the proxy temperature, since there is still bias with the delta 18O seawater. And the varying imprint of the Indo-Pacific climate mode on the SST and salinity of the Indonesian maritime region, as evident in Timor coral, should be taken into account when interpreting the paleoclimate record from Indonesia. And we still need the replication core from the IOD and the ENSO region, and also need more calibration study to improve the proxy calibration, and also the reconstruction of the paleoclimate parameters. Thank you. Sekian, terima kasih.
Okay, thank you so much, Professor. And this session is question and answer. Maybe participant, online participant or offline participant. Who asked to speak up? Raise your hand. Come on.
Assalamualaikum warahmatullahi wabarakatuh. Morning, Prof. My name is Vera. I am from Geophysics 2018, University of Bengkulu. I have a question. Is it in Bengkulu province? SST or NSSS are low or high? What is cause? Please explain, Prof. Thank you.
Could you repeat again?
Is it in Bengkulu province? SST or NSSS are low or high? What is cause?
You mean your question is whether the SST and SSS in Bengkulu is low or high?
Yes.
Well, it is we should. You mean in the Bengkulu waters, yeah? We should how can I say? to know the SST, of course, it's good if we measure, but there are some data from the reanalysis or from the satellite that we can see what is the status of the salinity and the SST and around Bengkulu waters. But here, what I mean is usually during the El Nino, for example, there will be a cooling SST around the southwestern Sumatra. That means also including Bengkulu. But to know, because this parameter is, of course, it changes by time also, and then to know this, you can look into the internet database. They are free at Lamon database. You can see the the variation of SST and also salinity in the time set through times.
Okay.
I hope that's answered.
Thank you, Prof.
Thank you. Another question? Maybe? Online participant? No. Okay, sir.
Mbak Yuda, this is Asar Lewis speaking.
Oh, thank you, Pak Asar.
Yeah, you saw the SST data from Nggano it's look like more negative compared to other, isn't it? You already saw time series SST from Nggano is more like negatively compared to other model, or what?
No, that is, I only select during the El Nino event and also during the IUD event. That's what I present in this. Maybe I just share. I will have, we can show you again here. So this means, this is only the composite map, and I only select for the negative IOD event. But during the normal condition, of course, this is changes also. But during the negative IOD event, we can during the positive IOD, the SST anomaly here will be negative anomaly. During the negative IOD, there is a warming here. So this is
Mbak Yuda, I mean
yeah?
From time series data. Not this slide.
This is,
From time
Which
series
one?
data from Nggano SST.
From time series.
SST data from Nggano.
Well, this one. This one. This is a time series from the Nggano coordinate. This one.
I guess in the beginning you talk, maybe not this slide.
Yeah, this one, huh?
No.
This one?
Okay,
This
okay.
one? Huh?
There is time series SST from Nggano, and then you saw also some comparison that with the model.
This is the for the time series is this is the time this is the time series SST from Nggano. This one.
Okay.
This
It's look like this is relative, or it's look like
no,
more
this is
negative.
the monthly. This one is the The black one is the monthly time series, and then the blue one is the anomaly data of the SST, which is mean seasonal remove. So I remove the seasonal variation in the time series data, so we can get more clearly changes of the SST.
Okay. Okay.
And this
I understand. My next question is, you say it's very hard to use stability stop 18 as a proxy of for sea surface temperature changing. Because it's contained stability stop from seawater. Do you think there are any way to isolate stability stop from seawater to get, that's the signal from climate change?
You mean as to remove the oxygen isotope seawater in the coral, and the oxygen isotope content in coral? But I think that it is how can I say? It is already naturally that the delta oxygen isotope in coral is influenced by the temperature and delta oxygen isotope seawater. That's why we cannot use that, but that is my opinion. Yeah? That's why we cannot use the delta oxygen isotope in coral only to reconstruct the temperature, but we have strontium calcium content in coral, so why we don't use just strontium calcium content in coral, which is convincing as the temperature? So that's my opinion.
Okay.
Because we can use coral oxygen isotope together with the strontium calcium in coral to reconstruct delta oxygen isotope seawater, and then from the delta oxygen isotope seawater reconstruction, we can also reconstruct the salinity. That's what usually people also done in the paleoclimatology.
Thank you, Mbak Yuda.
Okay. Thank you. Any question? No? Online participant? No? Okay, once again, thank you so very much for Professor Sriyati Cahyarini as invite speaker this conference.
You're welcome, thank you.
And certificate. Okay, Prof. This certificate as invite speaker.
Thank you for the certificate and for invitation to give a talk in this conference. Thank you Pak Ashar.
Terima kasih,
Mbak Yuda. Ya.
Terima kasih Pak Ashar.
Sama-sama.
Okay. At the end of the session, our activity for today ends. Thank you very much for all participants, maybe online or offline. See you and the next ICSAP 2023, insyaAllah. Assalamualaikum warahmatullahi wabarakatuh.
Okay, please give a round of applause.
Yes. For an excellent presentation from our last speaker.
Thank you for Professor Dr. Sri Yudawati Cahyarini for the invited speech.
Ladies and gentlemen, this is the end of our plenary session. Thank you for all the speakers and participants for your attention and participants.
For the next session is photo session. For the first, for all the offline participant, we invite to all participants in this room to come forward for the photo session. I repeat again, for all participants in offline to come forward to the stage for photo session. Once again, for all participants in offline, please come forward to the stage.
Bagaimana jadi penutupannya?
Setelah foto session.
Ada kata orang itu.
Tadi
Gimana sih dia caranya? Jelas.
makanya tadi saya temui Bapak.
Orang itu gimana?
Maybe for the lecture and the committee, the first, please to the all commits come forward to the stage. For all commits,
Please come to the stage. Sekali lagi disilakan kepada seluruh dosen dan tamu undangan untuk maju ke depan dan juga pihak para panitia untuk foto bersama.
okay, for the all participants, welcome to the stage.
Ayo, come on, hurry up.
All of you, please.
Maybe can sit. Oke, fotografer siap. 1, 2, 3. Okay, for the Zoom, can you open this camera? Open your camera because for the session. Okay, then for the Zoom, please, Mr. Professor, open camera.
We invite you online participants to open your camera for the photo session.
Okay, photo session.
Once again, for the online participants, we invite you to open your camera for the photo session.
Okay. Saya siap. 1, 2, 3. Okay. 1, 2, 3. The next slide in Zoom. 1, 2, 3. The next slide again in Zoom. 1, 2, 3. The next slide in Zoom. 1, 2, 3. Okay.
Okay, thank you for online
Okay,
participants.
thank you for all participants in Zoom, in online and offline. Thank you, Professor, Mr.
Attention please for all participants. We will continuing our agenda.
Please kindly be seated.
Okay, ladies and gentlemen, the next is closing speech will delivered by Vice Dean of Academic of Faculty of Mathematics and Natural Sciences will be referred by Mr. Ashar Mudalubis, PhD. The time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Honorable all participants for ICSAP 2022. In this occasion, on behalf of the Dean of Mathematics and Natural Sciences, I'd like to give a speech related to closing ceremony for this conference. In the last 2 days, we already invited several keynote speakers from various countries around the world. I think the topic is very relevant for what we're going right now. We're facing in Indonesia, especially in Bengkulu. We start from potential tourism, disaster threat, climate change, geoscience, renewable energy. I think that kind of topic is suitable for us to do the research in Bengkulu like this. But we have to highlight at least several things. For example, an indicator for success one conference, there are several lists. The first, of course, we come to the conference and then ask for question. We have discussion with the invited speaker, keynote speaker, as well as among participants. The second indicator is after we submit people proposing for this conference. The deadline is today, 10 September 2022. So the deadline is until midnight. So please submit your people, otherwise you cannot have chance to publish in IOP proceeding journal. And then the third keynote speaker, the third indicator is when we finish the conference, normally we have collaboration. We maintain to conduct collaboration with a speaker that we already seen yesterday. So how we create collaboration also is very important. Some speaker already offer for us for collaboration. Some speaker, they want to come to Bengkulu with their own ticket. For example, one speaker from UK also will come for collaboration. I think it's a good chance for us to continue the collaboration. If we success maintain building collaboration, of course, is one indicator that ICSAP 2022 is successful. And then, beside that, of course, students also try to connect with the speaker. What do you want to ask? Just email, find their name on the internet. It's very easy to find their name. And then you can send them a mail, try to build and connect with them, because they are very generous scientists around the world. So I think if we if we consider that indicator, we can, of course, eager for the next ICSAP. But if we stuck with this indicator in this year, I think it's very hard to go for the next ICSAP. On behalf of the committee, I would like also to thank
committee, for example, from our department, study program, student association, of course, all supporting from university, faculty of mathematics and natural sciences, University of Bengkulu. We'd like to thanks for support that we already received for this conference. If we have further question related to the conference, you can go to our website and then just send email to us. And then please keep in touch. We have ICSAP 2022 group, WhatsApp group. Just go there and then ask a question related to publication for this conference. Just that I have to say on behalf of Faculty Mathematics and Natural Science, University of Bengkulu, I would like to close this very fantastic and beautiful conference. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you for Mr. Asar Wilbis, PhD, for the speech. Ladies and gentlemen, we have done some of our agendas, and now we come to the last agenda, is closing. Before we close the program,
we are, as the master of ceremony, like to make an apology for our mistake. Also, thank you for attending this event. Again, let's give applause for all of us.
Wassalamualaikum warahmatullahi wabarakatuh. Goodbye and see you in the third ICSAP 2023.
Okay.
fokus adalah sepi. Acara keluarga.